promise is real. Most courses aren't. You've seen the demos. An AI agent that books meetings, writes emails, manages your inbox, browses the web, completely autonomous, completely capable. It looks like magic. Then you try to build one yourself. And it doesn't work the way the demos suggested. The outputs are unpredictable. The logic breaks. It hallucinates. You spend hours debugging something that looked trivial in a tutorial. Sound familiar? That's not a skill problem. That's an information gap. Most resources show you what AI agents can do. Almost none show you how to make them work reliably. This course closes that gap. Build an AI agent that works is a practical project-first course. By the end, you won't just understand AI agents conceptually. You'll have built one, a real one, something you can use, extend, and deploy. No theory-only lectures, no surface-level overviews, just the actual craft of building agents that do what you need them to do. What you'll build. You'll start with the foundations, how large language models reason, plan, and decide. Not from a textbook angle, from a builder's angle. Then you'll give your agent tools, real tools, web search, APIs, file access, the ability to act on the world, not just respond to prompts. You'll build the loops that let your agent think, act, check its work, and try again. You'll handle errors, edge cases, unexpected inputs, the stuff nobody teaches but every builder eventually hits. And throughout, you'll be working on a real project, not exercises, not toy examples, a working agent you built yourself. Who this course is for. You don't need a background in machine learning. You don't need to understand the math behind a transformer. You need to be comfortable writing code. You need to be genuinely curious about what AI can do in the real world. And you need to want to build something that actually functions. This course is for developers who want to ship AI-powered products, for entrepreneurs who want to automate the work that's eating their week, for technical professionals who can see where this is all going and want to get ahead of it. If that's you, you're in the right place. Let's get started. AI agents aren't a trend on the horizon. They're already changing how software gets built, how businesses operate, how work gets done. The gap between people who understand this and people who can build it is closing fast. This course puts you on the right side of that gap. It's hands-on, it's practical, it's built around one outcome. You finish with a working agent. Enroll today. Let's build something that works. The demo that impressed everyone and then failed. The demo was flawless. The room was buzzing. 3 months later, the project was quietly shelved. This is not a rare story. It happens inside organizations every week. An AI agent that looked extraordinary in testing delivers almost nothing in production. The question isn't why AI agents fail. The question is why impressive ones fail. And the answer has almost nothing to do with the technology. What you'll understand by the end of this lesson. This lesson is your first filter. Before you choose a use case, before you write a single requirement, you need to understand why the wrong starting point kills even technically excellent agents. By the end, you'll be able to spot the warning signs of a failing use case before the build starts. That saves months of work and protects your credibility. 3 root causes. That's all it takes. Let's go through each one. Root cause 1. The wrong process. The most common mistake is choosing a process that looks automatable, but isn't. Take email triage. It sounds perfect for an agent. High volume, repetitive, time-consuming. But email triage in most organizations relies on implicit knowledge. Knowing that the CFO's emails always jump the queue. Knowing that a certain supplier's urgent tag rarely means urgent. That knowledge lives in people's heads, not in any system an agent can access. An agent working from the surface of a problem will fail on the exceptions. And in a real organization, the exceptions are constant. The fix. Before choosing any use case, map the process end to end. Find where the implicit rules live. If they can't be made explicit, the agent will struggle. Root cause 2. Misaligned expectations. The second cause is a mismatch between what stakeholders expect and what the agent actually does. A customer service agent that handles 80% of queries brilliantly is a genuine success. But if the team expected 100%, and the remaining 20% require painful manual escalation, the agent feels like a failure. This isn't a technology problem, it's a communication problem. It gets set in the first conversation about the project. Set your expectations in writing before the build starts. Define what success looks like at 60%, at 80%, at 95%. Make those numbers visible to everyone with an opinion about the outcome. Root cause 3. No clear success metric. The third cause is the quietest and the most dangerous. A project with no defined success metric can never truly succeed. It can also never truly fail, which means it drifts until someone with budget authority decides they've seen enough. We want to improve the customer experience is not a success metric. We want to reduce average response time from 48 hours to 4 hours for 90% of inbound queries is specific, measurable, defined before a line of logic is written. That's what separates a project that can be defended from one that disappears at the next budget review. The pattern to break. Here's the pattern that causes most failures. Someone sees a compelling AI demo. They reverse engineer a use case to match it. The use case gets approved because it sounds innovative, and then reality arrives. The alternative is simple. Start with a problem, a real, painful, well-understood business problem. Then ask whether an agent is the right tool to solve it. In the next lesson, we'll give you the framework that makes that question answerable. 5 business cases. Every valuable agent fits one of them. If you can't place your idea in one of the 5, that's your first warning sign. 5 patterns. Every valuable agent fits one. Every agent project that delivers real business value does one of 5 things. It removes delay, it cuts cost, it lifts quality, it speeds up response, or it replaces repetitive human effort. That's it. 5 business cases. If your idea doesn't map to one of them, it's a solution in search of a problem. This lesson gives you those 5 patterns in detail, with examples you can match against your own context. Why this framework matters most. AI projects start with the technology. We have access to this model. What can we do with it? That's backwards. Value comes from the problem, not the tool. The 5 business cases framework keeps you problem first. By the end of this lesson, you'll be able to take any agent idea and immediately identify whether it has a legitimate business case or whether it's interesting without being useful. Case 1. Delay reduction. Delay kills businesses quietly. A proposal that takes 3 days to produce. A contract that sits in a queue for a week. An onboarding process that stretches across a month. Agents built for delay reduction attack waiting time. They work around the clock. They don't batch tasks. They don't wait for the right person to be available. Example, a legal firm where contract review took an average of 6 days. An agent reviewing standard contract clauses reduced that to under 4 hours. The lawyers still signed off, but the waiting disappeared. The signal for this case, people are waiting on something that could be processed faster without losing quality. Case 2, cost reduction. Case 3, quality improvement. Cost reduction is the most obvious case, and the one most often overstated. Agents don't eliminate headcount overnight. They reduce the cost per transaction for high-volume, well-defined tasks. Data entry, document classification, routing, first-pass review. The economics only work at scale, but at scale, they work very well. Quality improvement is subtler. This is where agents outperform tired humans. Consistency doesn't waver at 4 p.m. on a Friday. An agent applying the same classification logic to the 10,000th document as it did to the first. For compliance work, audit preparation, and quality control, this is the case. Case 4, response speed. Case 5, human effort. Response speed is about the customer experience of waiting, not internal delays, external ones. A customer who emails at 11 p.m. and gets a useful reply at 11:01 p.m. has a very different experience from one who waits until 9 a.m. Agents built for response speed handle the first layer of every interaction. They triage, they answer what they can, they escalate what they can't, with context already gathered. The human who picks it up isn't starting from scratch. Human effort reduction is the fifth case. It's not about replacing humans. It's about removing the tasks that drain them. The copy-paste work, the reformatting, the chasing. Free that time and people do the work that actually requires them. Apply the framework now. Take the use case you're considering. Write down which of the 5 it maps to. If you can name it clearly, delay, cost, quality, response, or effort, you have a business case. If it maps to none of them, stop. Go back to the problem. The technology will wait. In the next lesson, we'll give you a discovery technique that surfaces the highest value opportunities inside any organization. And it doesn't require a single stakeholder interview. Your best discovery tool is already in the building. You don't need a consultant to find your best agent opportunities. You don't need a process audit. You don't need a 2-week discovery workshop. You need to listen to what your employees complain about. The tasks people groan about are almost always the tasks that are high volume, low variability, and deeply frustrating. In other words, exactly the profile of a strong agent use case. What the complaint test finds, most organizations have 3 to 5 processes that almost every employee in a given team could describe as painful. Not broken, just tedious, slow, repetitive. These are the gold mines. They've survived because fixing them didn't seem worth the engineering effort. That calculus has now changed. By the end of this lesson, you'll know how to run the employee complaint test in under a day and walk away with a ranked shortlist of agent opportunities. How to run the test. Step 1. Pick a team. 1 team, 1 hour. Don't try to boil the ocean. Ask 4 questions. What task do you do most often that feels like a waste of your skills? What do you spend time on that you could hand off immediately if someone capable were available? What slows you down the most when you're trying to do your real job? What do you spend Sunday evening dreading about Monday? You don't need a formal survey. A team meeting, a whiteboard, and 30 minutes of honest conversation is enough. The complaints will surface fast. They always do. What to listen for? Not every complaint points to an agent opportunity. Some processes are painful because they require human judgment at every step. Those are not the ones you're looking for. You're looking for complaints that sound like this. I spend half my day doing the same thing over and over. We have to check the same information in 3 different systems. Someone always has to manually move this from one place to another. Repetition, volume, predictability. Those 3 words are the signal. When a complaint contains all 3, you're looking at an agent opportunity. Prioritize the shortlist. After the session, you'll likely have 5 to 15 complaints. Not all of them are equal. Score each one on 3 criteria. How often does it happen? Daily scores higher than monthly. How long does it take? Hours scores higher than minutes. How much does it depend on judgment or relationships? Low dependency scores higher. The highest scoring complaints become your shortlist. These are the processes where an agent can deliver the fastest, most visible impact. Take the top 3 into the next lesson. We'll use a second filter to find your strongest first build. A word on resistance. Some employees won't want to share their complaints. Not because they don't have them, because they're worried about what automation means for their role. Address that directly. Be clear that the goal is to remove the tasks that waste their time, not to remove them. The agent handles the routine. They handle what actually requires them. When people believe that, the complaints flow. And so do the opportunities. Your first build should be boring. Everyone wants to build something impressive first. A sophisticated reasoning agent, a multi-step autonomous workflow, something you can put in a press release. That instinct will slow you down. The first agent you build should be boring. High volume, well-defined, and low stakes. Not a moonshot, a proof point. This lesson gives you the 7 archetypes of a strong first agent build, so you can match your shortlisted opportunities against a proven profile. What makes a strong first build? 3 criteria: volume, clarity, and reversibility. Volume. The process needs to happen enough that the agent gets real-world exposure fast. 100 interactions a week is useful. 100 a day is better. Clarity. The rules for doing the task well must be expressible in plain language. If you can't explain the logic to a new hire in an afternoon, you can't encode it in a system prompt. Reversibility. When the agent gets it wrong, and it will sometimes, the mistake must be fixable. No agent should have unchecked authority over something irreversible on its first deployment. Archetypes 1 through 3. Curious. Archetype 1. High volume customer interactions. Inbound queries. FAQ responses. Appointment handling. High frequency, well understood rules, and a human fallback already in place. This is the most common first build, and for good reason. Archetype 2. Document-heavy workflows, contract review, invoice processing, compliance checking. Agents that read, classify, and extract from documents are mature and reliable. The documents provide structure. The structure reduces hallucination risk. Archetype 3. Research and synthesis, competitor monitoring, market summarization, pre-meeting briefings. The output is informational. It informs a human decision rather than making one. Lower stakes, higher tolerance for imperfection. Archetypes 4 through 7. Curious. Archetype 4. Sales and lead qualification, scoring inbound leads, drafting first touch outreach, routing qualified prospects. High volume, clear criteria, and the output is a recommendation, not a commitment. Archetype 5. Internal operations and support, HR query handling, IT help desk triage, policy lookup. Internal users are more forgiving than customers. This makes it an excellent proving ground. Archetype 6. Content generation and editing, first drafts, reformatting, proofreading to a style guide. The human always reviews before anything goes out. Low autonomy, high leverage. Archetype 7. Data classification and routing, tagging support tickets, categorizing survey responses, routing emails. Purely mechanical, highly repetitive, and almost always high volume. The fastest return on effort of any archetype. Score your shortlist. Take the top 3 complaints from the last lesson. Match each one to the archetype it most resembles. If it doesn't resemble any of the 7, treat that as a warning sign. Then score each remaining candidate against volume, clarity, and reversibility, out of 10 on each dimension. The highest total score is your strongest first build. This isn't a perfect formula. It's a structured way to make a better first decision. The mindset that makes first builds succeed. Your first agent build is not a product launch. It's an experiment with teeth. The goal is a system that works reliably, generates useful data, and builds internal confidence that more ambitious builds are worth attempting. Resist scope creep. Resist the urge to add features before the core behavior is proven. A narrow agent that does one thing brilliantly is more valuable than a wide one that does 3 things inconsistently. In the next section, we'll define exactly what that one thing is, with precision. The most expensive page you'll ever skip. Most agent projects that go wrong don't go wrong in the build. They go wrong before a single line of logic is written. They go wrong because nobody wrote down what the agent was supposed to do. Not really, not precisely. The agent brief is a 1-page document that fixes that problem. It takes 90 minutes to write. It saves months of rework. What the brief contains. 6 elements. Each one answers a question the build will eventually force you to answer anyway. Write them down now or answer them under pressure later. Purpose. What problem does this agent solve and for whom? Stakeholders. Who benefits? Who oversees? Who can stop the project? Constraints. What can the agent never do, regardless of instructions? Success criteria. What does good look like in measurable terms? Failure conditions. What outcome would cause us to stop the agent immediately? Review cadence. When will we formally assess whether the agent should continue, expand, or change? Writing the purpose statement. The purpose statement is the hardest element to write well. Not because it's complex, because it requires precision. A weak purpose statement. The agent will handle customer queries. A strong one. The agent will respond to inbound product support queries by email within 2 minutes, resolving standard FAQs without escalation and routing complex issues to the relevant human with a structured context summary. The strong version contains a trigger, a task, a standard, and a boundary. Every word is doing work. That's what you're aiming for. Success criteria and failure conditions. These two elements sit across the table from each other. Success criteria define the outcome you're building towards. Failure conditions define the line you won't cross. Good success criteria are specific and testable. Customer satisfaction score above 4.2 out of 5 for agent-handled queries. Escalation rate below 20% of total inbound volume. Average response time under 90 seconds. Failure conditions protect you when things go unexpectedly wrong. If the agent generates a response that includes pricing commitments, halt and review. If weekly escalation rate exceeds 40%, pause autonomous operation. These aren't pessimistic, they're professional. Getting stakeholder sign-off. The brief is not a solo document. It needs to be read, challenged, and signed off by everyone who will have an opinion about the outcome. That includes the team whose work the agent touches, the person who controls the budget, any compliance or legal function with an interest in the output. And if the agent interacts with customers, a representative from whoever owns customer experience. Sign-off takes a meeting. One meeting with the document on screen, working through each element. Disagreements surface there, not 6 weeks into the build. The brief as a living document. The brief is not filed away after sign-off. It's the reference document for every decision made during the build. When someone suggests adding a new capability, check it against the brief. When a scope question arises, the brief answers it. When the build is complete, the brief is the acceptance test. 1 page, 90 minutes. The most valuable thing you will produce before the build starts. In the next lesson, we'll go deeper into the structure of what the agent actually does. The 4 elements of agent workflow. 4 elements. Every agent has all of them. Every agent workflow, regardless of complexity, industry, or technology stack, contains 4 elements. The trigger, the task, the output, the handoff. Miss one and the design has a hole that shows up in production, not in testing. This lesson walks through each element in detail. By the end, you'll use these 4 as a design checklist for any agent you build. Element 1, the trigger. The trigger is what starts the agent. It's simple to define, but critical to specify exactly. Is the agent triggered by an incoming email, a form submission, a database record crossing a threshold, a scheduled time, a human clicking a button? Each trigger type has different implications for latency, reliability, and error handling. The most common design failure here is an ambiguous trigger. The agent runs when new data arrives. What counts as new? How often is it checked? What happens if data arrives while the agent is still running on the previous batch? Specify the trigger until there's no room for interpretation. Element 2, the task. The task is what the agent does between the trigger and the output. This is where most of the design work lives. A well-defined task has 3 properties. It's bounded. The agent knows what's in scope and what isn't. It's sequential. The steps have a defined order. It's testable. You can construct a scenario that proves the task was completed correctly. Many agent designs fail because the task is described at the wrong level. The agent handles the query is a category, not a task. The agent reads the query, searches the knowledge base for matching content, generates a response using that content, checks the response against the tone guide, and sends, unless a prohibited topic is detected, is a task. Element 3, the output. The output is what the agent produces. It sounds obvious. It rarely gets specified precisely enough. Define the output in terms of format, length, recipient, and channel. Is it a reply email, a structured JSON record, a Slack message, a PDF report? Who receives it? Where does it go? What system needs to consume it? Also define what a bad output looks like. What should the agent produce when it can't confidently answer? A graceful failure is part of the output specification. Don't leave it to chance. Element 4, the handoff. The handoff is what happens when the agent reaches its limit. Every agent has a limit. Designing the handoff is acknowledging that. A good handoff has three qualities. It's triggered by a clear condition, not a vague "when it gets complicated." It passes context. The human who picks it up knows exactly what the agent did and why it stopped. It's fast. The transition from agent to human doesn't introduce a delay that defeats the purpose of the agent. The handoff is also where your damage limitation strategy lives. We'll build that out in section 3. For now, make sure every agent design you produce has a defined handoff condition. Use the 4 elements as a checklist. Before any agent goes into detailed design, run it through the 4 elements. Can you describe the trigger precisely? Can you describe the task as a testable sequence? Can you specify the output in terms of format, recipient, and failure state? Can you define the handoff condition and the context it passes? 4 yes answers means the design is ready to develop. A no anywhere means there's a gap that will cost you later. Next, we'll talk about the boundary that protects the agent from doing too much. Scope boundaries. What your agent must never do. Every agent design has 2 parts: what the agent does and what the agent never, under any circumstances, does. Most teams focus intensely on the first part. The second part is usually written as an afterthought, if it's written at all. That's a mistake. Scope boundaries are not a constraint on your agent's capability. They are a guarantee of its reliability. Why boundaries matter more than features. An agent without clear boundaries will eventually do something unexpected. Not malicious, just unanticipated. A customer service agent that offers a refund when no refund policy applies. A data processing agent that overwrites a record it was only supposed to read. A scheduling agent that books a meeting on a day the user had blocked. These aren't edge cases. They're the natural consequence of underspecified boundaries. The agent is doing exactly what it was implicitly permitted to do. The problem is that nobody made the permission explicit. Hard boundaries versus soft boundaries. Not all boundaries are equal. Some are absolute, some are conditional. Hard boundaries are non-negotiable. The agent never takes a payment action. The agent never modifies a customer record. The agent never sends an external email without a human review step. These are written into the design and cannot be overridden by any instruction. Soft boundaries are defaults that can be adjusted. The agent doesn't respond outside business hours, unless the configuration is changed for a 24/7 product. The agent doesn't discuss competitor pricing unless marketing specifically enables that capability. Soft boundaries give you operational flexibility without removing the safety layer. How to define your boundaries. Start with the question, what would a reasonable stakeholder be alarmed to see this agent do? Work through scenarios. What if a user asks the agent to refund their entire order history? What if the agent receives a message that appears to be from an internal system, asking it to skip the verification step? What if the task takes twice as long as expected? Does it keep running? Every scenario that alarms you is a boundary to define. Write each one as a specific prohibition. The agent will not, followed by a precise description of the prohibited action. Document boundaries before the build. Boundaries defined after a mistake are reactive. Boundaries defined before the build are protective. Your agent brief from the previous lesson has a constraints field. That's where hard boundaries live. Every developer, every prompt engineer, every stakeholder reviewing the design should be able to read those constraints and understand them without interpretation. No jargon, no ambiguity. The agent cannot initiate outbound calls is a boundary. The agent should be careful about calls is not. The confidence that boundaries create. Here's what well-defined boundaries actually give you. The confidence to let the agent run. A team that is afraid of what their agent might do will restrict it so heavily that it can't do its job. A team that has defined clear boundaries can deploy with confidence and expand those boundaries as trust is established. Clear boundaries make autonomous operation possible. Without them, you'll always be watching over the agent's shoulder. In the next lesson, we'll translate your scope thinking into a single, testable goal statement. One sentence that decides everything. Every build decision you make, what tools to connect, how to write the system prompt, how to define the handoff, should be answerable by a single sentence. That sentence is the goal statement. It's not a mission statement, it's not a vision, it's a precise, testable description of what this agent must achieve. If your team can't agree on the goal statement, they're building in different directions. What a good goal statement contains 4 components: the actor, the action, the standard, the condition. The actor, what the agent does. The action, the specific behavior. The standard, what good performance looks like. The condition, in what context and with what constraints. Put together, the agent classifies inbound support tickets by category and priority, achieving 95% agreement with human reviewers for English language tickets submitted through the web portal. Every word is load-bearing. If you can remove a word without losing meaning, remove it. Common goal statement mistakes. Mistake 1, too broad. The agent improves customer experience. How? For whom? By how much? Unmeasurable, unfalsifiable, useless as a design anchor. Mistake 2, too narrow. The agent replies to emails about invoice numbers. This is a feature, not a goal. It tells the developer what to build, but not why or how well. Mistake 3, compound goals. The agent handles support queries and qualifies leads and updates the CRM. 3 agents, not 1. A goal statement with "and" in the middle usually means the scope needs splitting. How to write yours. Start with the process you identified in section 1, the one that scored highest against volume, clarity, and reversibility. Draft the actor and action first, the agent. Then add the standard, achieving, then add the condition, for, read it aloud. If you stumble over it, it's too complex. If you finish it and immediately think, but what about? Add the exception or create a separate scope boundary. The goal statement as your acceptance test. When the build is complete, the goal statement becomes your acceptance test. Can you run the agent against a representative sample and measure whether it hit the standard? If yes, the goal statement is well formed. If you have to judge whether it's roughly right, it isn't. This is why the standard must be measurable. Not good quality responses. Quality measured how? By whom? Against what rubric? At what frequency? Precision here saves you from the most common project ending, a launch where nobody can agree whether it worked. One statement, shared understanding. The goal statement should appear at the top of your agent brief. It should be on the first slide of any stakeholder update. It should be what every team member can recite without looking at notes. That's not ceremony, that's alignment. And alignment is the thing most agent projects never quite achieve. In the next lesson, we'll run your design through the alignment test, a structured check that confirms your goal, your business need, and your user experience are all pointing the same direction. 3 things that must point the same direction. An agent can be technically correct and still fail. It can meet its goal statement, it can work within its scope boundaries, and it can still frustrate users and miss the business need. The alignment test catches that before the build. It checks that 3 things are pointing the same direction: the agent goal, the business need, and the user experience. If any of the 3 is misaligned, the others can't save it. Check 1. Does the goal serve the business need? The business need is the reason the project was approved. Cost reduction, faster response, higher quality, removed friction. Your goal statement should be directly traceable to one of these. Ask this question: if the agent hits its goal statement perfectly, does the business problem get solved? Sometimes the answer is mostly, but not entirely. That gap is useful information. Either the goal needs adjusting, or the project scope needs a second phase defined up front. A goal that is technically achieved but doesn't solve the business problem is the most expensive kind of success. Check 2. Does the goal serve the user? This check is often skipped. The user, the person who interacts with the agent directly, is not always the stakeholder who commissioned it. A manager might commission an agent to save processing time. The employee using it might experience it as an additional step in their workflow. The net effect: time wasted, satisfaction reduced, adoption abandoned. Before the build, answer 3 questions from the user's perspective. Does this agent make my job easier or harder? Does the output it produces actually help me, or does it create more work? Would I trust this agent to handle this, or would I rather do it myself? If any answer is unfavorable, the design needs revision, not the user. Check 3. Does the experience match the promise? The experience check asks, does what the agent does match what users were told it would do? Expectation gaps are where trust breaks down. An agent marketed as instant support that takes 40 seconds to respond. An agent described as intelligent that gives the same scripted response to wildly different questions. An agent called proactive that only reacts. Before launch, write down what you'll tell users about the agent. Then test whether the actual behavior matches. If it doesn't, either adjust the communication or improve the behavior. Don't hope users won't notice. Running the full alignment test. 3 checks, 3 questions each. Run it in a team of 3 or 4 people, including at least one person who represents the user's perspective. Score each check on a simple scale: aligned, partially aligned, or not aligned. Any not aligned is a blocker. Any partially aligned is a risk to document and mitigate. Full alignment across all 3 means your design is ready to move into detailed build planning. Alignment is not agreement. The alignment test doesn't require everyone to love the design. It requires everyone to agree on what the agent will and won't do, and to confirm that the outcome serves the people it's meant to serve. Disagreement during the alignment test is not failure, it's discovery. Surface it now, resolve it now, and build with clarity. Section 2 is complete. You now have an agent brief, a workflow design, defined scope boundaries, a testable goal statement, and confirmed alignment. That's more preparation than most agent projects ever do. In Section 3, we'll add the layer that most builders skip: damage limitation. When the agent does something you didn't expect. An autonomous agent is doing things on your behalf, while you're in another meeting, while you're asleep, while nobody is watching. That's the point, but it's also the risk. When an agent makes a mistake at scale, the mistake scales with it. Damage limitation is the discipline that keeps that from happening. It's not pessimism, it's professional engineering. What damage limitation actually means? Damage limitation is not about making agents slow or overly cautious. An agent that asks for confirmation at every step is not safe. It's useless. Damage limitation means designing the agent so that when it makes a mistake, and it will, the mistake is detectable before it causes harm, reversible before it becomes permanent, contained so it doesn't cascade. Those 3 properties, detectable, reversible, contained, are the engineering target for every agent operating with meaningful autonomy. The spectrum of agent mistakes. Not all mistakes are equal. A misclassified email is annoying. A sent apology to the wrong customer is embarrassing. An unauthorized financial commitment is a legal problem. Damage limitation design starts by mapping the mistake spectrum for your specific agent. List every action the agent can take, then score each one. How bad is it if the agent gets this wrong? Low, medium, or high severity? High severity actions need gates. Medium severity actions need logging and rapid recovery. Low severity actions can be trusted to run freely. Design the controls to match the stakes, not to a blanket policy. 3 practical controls. Control 1. Human in the loop checkpoints. For high severity actions, a human must approve before the agent proceeds. This is not the agent failing, this is the agent knowing its limits. Control 2. Dry run mode. Before the agent runs in production, it runs in simulation. It shows you what it would have done without doing it. Review the dry runs, fix the surprises, then go live. Control 3. Rate and scope limits. The agent can only act on N records per hour. It can only modify files in a specific folder. It can only send to addresses on an approved list. Limits prevent the agent from amplifying a bad decision before anyone notices. Damage limitation is a design conversation. These controls need to be decided before the build, not discovered after an incident. Bring together the people who understand the business risk, legal, compliance, operations, and whoever will be held accountable if something goes wrong. For each high-severity action the agent can take, agree on the control that applies. Write it into the agent brief under constraints. Build it into the system before any autonomy is granted. The mindset behind the discipline. Damage limitation is how you earn the right to give agents more autonomy over time. You start with tight controls. You monitor closely. You loosen the controls as the evidence of reliability accumulates. An agent that has been operating cleanly for 3 months under tight controls has earned more trust than one deployed at full autonomy from day one. Trust is built through track record. The controls make the track record possible. In the next lesson, we'll give you a specific test for classifying the reversibility of any agent action. Can you undo it in 5 minutes? That's the test. One question, applied to every action your agent can take. Can a human undo this action in under 5 minutes, with no external dependency and no lasting consequence? If yes, the action is reversible. If no, it needs a gate. Why reversibility is the right frame. Risk assessment in technology usually focuses on probability. How likely is the agent to get this wrong? Reversibility focuses on consequence. If the agent gets this wrong, how bad is the damage and how quickly can we recover? A low probability mistake with irreversible consequences is more dangerous than a high probability mistake that can be fixed in seconds. Design for consequence, not just probability. The reversibility spectrum. Fully reversible. The action can be undone instantly by any team member. Sending a draft email to a staging folder. Adding a tag to a record. Generating a document that hasn't been sent yet. These actions can run freely. Partially reversible. The action can be undone, but it takes effort or has some residual impact. Sending a customer notification. Updating a CRM record. Scheduling a meeting. These need logging and ideally a short confirmation window before they execute. Irreversible. The action cannot be meaningfully undone. Sending a contract with commercial terms. Deleting records. Making a payment. Posting publicly. These require human approval. Full stop. Applying the test to your design. List every action your agent can take. Classify each one. Fully reversible, partially reversible, or irreversible. For every irreversible action, add a required human approval step. For every partially reversible action, add a confirmation window and automatic logging. For fully reversible actions, let the agent run. This creates a tiered control structure that matches the actual risk profile of your agent. Not a blanket restriction, not reckless openness, proportionate control. Document the classification. Serious. The reversibility classification should live in your agent brief under the constraints section, not in someone's head, not in an internal Slack thread, in the document that governs the build. When the build team sees send external email, irreversible, requires approval, they know exactly what control to build. When a stakeholder asks why the agent pauses before sending, the answer is already written down. The rule that protects you. Here is the rule. No agent gets unchecked autonomy over irreversible actions on its first deployment. Not on day one, not in week one, not until the track record justifies it. The reversibility test isn't a barrier to deployment. It's the mechanism that makes deployment safe. Safe deployment is fast deployment, because you don't spend 6 weeks getting legal sign-off on a system that couldn't hurt anyone anyway. In the next lesson, we'll look at how agents earn the right to operate with less supervision over time. Autonomy is earned, not granted. Every new agent starts with low autonomy. That's not a limitation. That's the right starting position. Autonomy is the product of trust. Trust is the product of evidence. Evidence comes from supervised operation over time. Earned autonomy is the framework for moving an agent from supervised to independent, systematically, with data at every step. The 3 stages of agent autonomy. Stage 1, supervised. Every output is reviewed by a human before it takes effect. The agent drafts, the human approves. This stage generates the baseline data you need to make informed decisions about stage 2. Stage 2, monitored. The agent acts autonomously, but every action is logged and reviewed on a defined schedule, daily, weekly, or per batch. Human oversight shifts from pre-approval to post-review. Stage 3, trusted. The agent operates independently. Exceptions and anomalies are flagged automatically. Humans review exception reports rather than individual outputs. This is the stage most agents aspire to. Few reach it before at least 3 months of stage 2. The promotion criteria. Moving an agent from one stage to the next requires evidence, not faith. Define your promotion criteria before the agent goes live. Typical criteria for stage 1 to stage 2. Human reviewers have agreed with 95% or more of the agent's outputs for 30 consecutive days. No irreversible errors have occurred. The stakeholder responsible for the process has signed off on the move. Typical criteria for stage 2 to stage 3. Exception rate has been below 2% for 60 days. All exceptions have been minor and self-contained. The monitoring infrastructure is in place to catch anomalies in real time. What gets measured? 3 metrics drive the earned autonomy decision. Agreement rate. What percentage of the agent's outputs match what a human reviewer would have produced? Exception rate. What percentage of the agent's actions trigger a flag or require manual intervention? Recovery time. When the agent does get something wrong, how quickly is it detected and corrected? These are not aspirational targets. They are production requirements. An agent that doesn't hit them doesn't move to the next stage, regardless of how long it has been running. What earned autonomy is not. Earned autonomy is not a one-way door. An agent that regresses due to a model update, a change in input volume, or a shift in the underlying process can and should move back to a more supervised stage. This is not failure. It's a control system working as designed. Autonomy that has been earned can be temporarily withdrawn when conditions change. It's restored again when the evidence supports it. Building confidence that compounds. Every week an agent operates cleanly is a week of evidence that a more ambitious build is possible. Organizations that use earned autonomy consistently find that internal resistance to AI agents drops. Not because people are convinced by arguments, but because they've watched the system work. Start supervised. Measure carefully. Move stages when the data says so. That's how you build the kind of trust that creates space for the next agent and the one after that. In the next lesson, we'll translate damage limitation into concrete design rules with the scoping principle. Least privilege, maximum trust. The scoping principle comes from computer security. Give any system, human or machine, only the access it needs to do its job, no more. Applied to AI agents, the principle is simple. The agent gets the minimum permissions, tools, and data access required to complete its defined task. Nothing extra, nothing just in case. Minimum scope creates maximum trust. Because when an agent can only do 10 things, you can test all 10. You can monitor all 10. You know exactly what you're accountable for. 3 dimensions of scope. Scope applies in 3 dimensions. Data access. What information can the agent see and read? Action authority. What can the agent do, write, send, or change? Tool access. What systems, APIs, and functions can the agent call? Define each dimension explicitly for your agent, not by listing what the agent can't do, by listing only what it can. Everything not on the list is implicitly prohibited. This is the only direction that is safe. Scope creep, the invisible risk. Scope creep in agent design is not a project management problem. It's a safety problem. It usually starts with a good intention. The agent can see the CRM, so let's give it access to the billing system while we're at it. We've already connected the email tool. Let's let it send from the main domain instead of the support alias. Each addition sounds small. Collectively, they create an agent whose capabilities nobody has fully mapped. An agent whose actions can no longer be fully anticipated. An agent that is harder to audit, harder to explain to stakeholders, and harder to recover when something goes wrong. Forced confirmation steps. For actions that sit on the boundary of acceptable risk, build in a confirmation step. Not a full human-in-the-loop approval, a pause and a check. Example, before sending any external email, the agent logs the draft and waits 30 seconds. A simple automated check runs. Is the recipient on the approved list? Is the content within defined parameters? If both pass, the email sends. If either fails, the action is held for human review. A 30-second pause prevents almost all the embarrassing mistakes. The agent loses almost nothing in efficiency. You gain a layer of protection that would take weeks to recover from if you'd skipped it. Automatic escalation triggers. Design the conditions under which the agent automatically stops and asks for help. These are not failure conditions. These are intelligent stopping points. Examples. The agent has processed more than X records in a single session. Flag for review before continuing. The agent has encountered more than Y errors in the past hour. Pause and alert. The agent has received a message containing specific keywords. Escalate immediately. Each trigger is a line in your design document before it's a line in your code. The scoping principle summarized: minimum permissions, explicit capability lists, three-dimensional scope definition, forced confirmation on boundary actions, automatic escalation triggers. These 5 rules, applied consistently, give you an agent that does exactly what you designed and nothing you didn't. They are the practical translation of damage limitation into a working system. Section 3 is complete. In Section 4, we go inside the agent itself, the 9 components that every production agent is built from. The most expensive conversation in any agent project. Which model should we use? This question gets asked early, it gets debated passionately, and it's almost never the most important decision in the build. But it is a decision you have to make well, because choosing the wrong model class costs you money, time, or quality, sometimes all 3. This lesson gives you a clear framework for making that choice. 2 classes of model, 2 broad categories: standard models and reasoning models. They are not better and worse versions of the same thing. They are built for different types of task. Standard models: fast, cost-effective, strong at language tasks, following instructions, generating text, classifying content, summarizing documents. They produce output in a single forward pass, quick, scalable, economical. Reasoning models: slower, more expensive, designed for multi-step logic. They think before they speak, working through a problem step by step before producing output. More reliable on tasks that require held context, conditional logic, or sequential decision-making. When to use a standard model. Use a standard model when the task is well defined, the inputs are predictable, and speed or cost is a priority. Customer query responses, document classification, email drafting, content moderation, data extraction from structured sources. These tasks have clear right answers. A standard model with a well-written system prompt will handle them reliably and cheaply. The mistake to avoid: using a reasoning model on tasks that don't require it. You pay 3 to 10 times more per token. You accept 2 to 5 times the latency, and you get approximately the same output. Don't over-engineer the model choice. When to use a reasoning model. Use a reasoning model when the task requires the agent to hold multiple pieces of information simultaneously and apply conditional logic across them. Complex contract analysis, where clause interactions matter. Multi-step research synthesis, where conclusions depend on earlier findings. Troubleshooting flows, where the correct action depends on a chain of diagnostic results. Financial analysis, where assumptions compound. The reasoning model earns its higher cost on tasks where a standard model consistently makes subtle errors that only become visible downstream. If you're not seeing those errors, you don't need the reasoning model. How to choose without guessing. Start with a standard model. Run your task against it. Review the outputs carefully. Look for errors in logic, missed dependencies, or conclusions that don't follow from the inputs. If you find systematic errors of that type, switch to a reasoning model and run the same task. Compare the outputs. If the reasoning model fixes the errors, justify the cost. If it doesn't, stay with the standard model and improve the prompt instead. Test before you commit. The model choice is one of the cheapest experiments in the entire build. The choice is not permanent. Model technology moves quickly. A task that required a reasoning model 6 months ago may be well within the capability of a standard model today. Review your model choice quarterly. The economics of getting this wrong are significant at production scale. Also, the model is one of 9 components. A brilliantly chosen model with a poorly written system prompt will still fail. In the next lesson, we'll go deep on the component most builders underestimate, the system prompt. The most read document your agent will ever see. The system prompt is read by your agent on every single interaction, every one. Before the user's message, before any tool is called, before any response is generated. It is the most influential document in your entire build. And most teams spend less time on it than they spend on naming the project. This lesson gives you the anatomy of a system prompt that actually works, and the technique that unlocks consistent behavior. The 6 sections of an effective system prompt. Section 1. Role definition. Who is this agent? Not a name, a description of its function, its expertise, and its relationship to the user. You are a support agent specializing in product billing queries for You help customers understand their invoices, payment methods, and subscription options. Section 2, Core Task Description. What does the agent do? Written as a sequence, not a list of capabilities. When a customer contacts you, you first identify whether their query relates to billing, subscription changes, or a technical issue. If billing or subscription, you handle it. If technical, you escalate. Rules, constraints, and tone. Section 3, Rules. The explicit do's and don'ts. Written as declarative statements. Always verify the customer's account number before discussing any account details. Never commit to a refund amount without checking the refund policy document. If a customer uses abusive language, issue one warning before ending the conversation. Section 4, Constraints. The hard limits. You do not have access to payment processing. Do not attempt to issue refunds directly. You cannot modify subscription tiers. Direct the customer to the account settings page. Section 5, Tone and Voice. How the agent communicates. Warm and professional. Use the customer's name where known. Avoid jargon. Keep responses under 150 words unless a detailed explanation is specifically requested. Output format and few-shot examples. Section 6, Output format. What the response should look like. All responses must begin with a one-sentence acknowledgement of the customer's query. End every response with a clear next step or a question that moves the conversation forward. Then, few-shot examples. 2 or 3 examples of ideal input-output pairs. This is the most powerful tool in system prompt writing and the most underused. An example does more to shape agent behavior than 3 paragraphs of instructions, because examples show the agent what good looks like. Instructions tell it. Examples demonstrate it. Writing few-shot examples. Each few-shot example contains 3 parts: the user message, the correct agent response, and, optionally, the reasoning the agent should apply. Choose examples that cover your most common cases and your most important edge cases, not examples that confirm the easy path. Examples that show the agent how to handle the situations where getting it wrong would hurt. 3 strong examples will outperform 10 weak ones. Quality over quantity. Spend more time on this section than any other. The system prompt is a living document. The first version of your system prompt will not be your best. It will improve with every test run. Every failure in testing is a gap in the prompt. Fill the gap, retest, refine. Version control your system prompts. Date them. Test each version against the same inputs. Track which version produces the best outputs. Treat it with the same rigor you apply to your codebase. In the next lesson, we'll look at the 4 specific failure patterns that emerge from poorly written prompts, and how to diagnose them before they reach production. Most production failures start with the prompt. When an agent fails in production, the instinct is to blame the model, change the model, switch providers, add more compute. In most cases, the model isn't the problem. The problem is in the system prompt, and it falls into one of 4 patterns. Learn to recognize these 4 patterns, and you'll diagnose failures in minutes, not weeks. Pattern 1. Vague rule definition. The rule exists, but it's too vague to be applied consistently. Be helpful but professional. What does that mean when a frustrated customer is swearing? Handle urgent queries faster. What's the threshold for urgent? Who defines it? How much faster? Avoid sensitive topics. Which ones? In what context? What counts as avoidance? Every vague rule is a decision the agent makes independently every time it encounters the situation. Sometimes it decides correctly, sometimes it doesn't, and the results are inconsistent in ways that are very difficult to debug. The fix: replace every vague rule with a specific, testable instruction. If a customer uses profanity, respond once with, "I'm here to help. I just need us to keep the conversation respectful." If it continues, close the conversation with the standard de-escalation message. Pattern 2. Missing examples. Instructions tell the agent what to do. Examples show it. When examples are missing, the agent interprets instructions through its training, which may not match your context. You write, keep responses concise. The agent has seen thousands of definitions of concise. Without an example, it picks one. Maybe that's 3 sentences. Maybe it's 3 paragraphs. You won't know until it's wrong. The fix. For every instruction that involves a quality judgment, length, tone, format, depth, add at least one example of the correct output. The example is the definition. Pattern 3. No stop condition. Every task needs a definition of done. When the agent reaches it, it stops. Without a stop condition, agents do one of 2 things. They stop too early with incomplete output, or they keep going, generating, extending, clarifying, until they run out of context or produce something incoherent. The stop condition is the task is complete when. Make it explicit, make it testable. Agents, like people, perform better when they know what finished looks like. Pattern 4, conflicting rules. This is the quietest failure pattern and the hardest to diagnose. 2 rules that individually make sense but contradict each other in specific situations. Always respond in under 150 words. Always explain the full process when a customer asks about a refund. A refund explanation might require 300 words. What does the agent do? It tries to do both. It compresses, it omits, it produces a response that satisfies neither rule. The fix: audit your rules in pairs. For every rule, ask, is there another rule that could conflict with this under specific conditions? Where conflicts exist, add a priority statement. If a rule about response length conflicts with a rule about completeness, prioritize completeness. A diagnostic before every launch. Before any agent goes to production, run a prompt audit against these 4 patterns. Read every rule. Is it specific and testable? Count your examples. Is there at least 1 per quality judgment? Find your stop conditions. Are they explicit? Check your rules in pairs. Do any conflict? This takes 40 minutes. It prevents failures that would take 4 weeks to diagnose and fix in production. Do it every time. Next, we'll look at something that shapes every agent interaction before the system prompt even runs: context engineering. Every token has a job. Every large language model has a context window, a fixed amount of information it can hold at once. Think of it as the agent's working memory. What goes in determines what the agent knows. What it knows determines what it does. Context engineering is the discipline of deciding what goes into that window. Every token in the context window should be doing useful work. Tokens that don't contribute to the task are tokens that crowd out tokens that do. This is not a technical concern. It's a design decision, and it shapes agent performance more than most builders expect. What lives in the context window? The context window holds several things simultaneously: the system prompt, the conversation history, any retrieved documents or knowledge-based content, the current user message, tool results from previous steps in the workflow. Each of these competes for space. A long conversation history crowds out retrieved documents. A bloated system prompt leaves less room for the data the agent needs to do its job. Context engineering is the process of making deliberate trade-offs between these elements. What to include? Include what the agent needs to make the right decision for this specific interaction. The current user message, always. The system prompt, always. Retrieved content that is directly relevant to this query, yes, but filtered. Recent conversation history, yes, but not the entire history for long conversations. Tool results, yes, but structured for readability. The test. If you remove this piece of information from the context, would the agent's output change for the worse? If yes, it belongs. If no, take it out. What to compress or remove? Old conversation turns that are no longer directly relevant to the current question. Full document content when only a specific section is needed. System metadata that was relevant to a previous step but not this one. Repetitive information that has already been established earlier in the conversation. Compression is not deletion. A 5-message conversation history can be summarized to a 2-sentence context note. The agent retains the meaning without consuming the tokens. Build summarization into your context pipeline for long-running conversations. Retrieval, augmented context. For agents that answer questions from a knowledge base, product documentation, policy manuals, support articles, The context doesn't contain the whole knowledge base. It contains the most relevant sections. Retrieval Augmented Generation, or RAG, is the mechanism that finds those sections. A search index identifies the most relevant content. That content is injected into the context window for the specific query. The agent answers from what was retrieved, not from general training. Quality of retrieval determines quality of answer. A well-built retrieval system gets the right context to the agent reliably. A poorly built one fills the context with plausible but wrong content. Retrieval quality is worth investing in. Context engineering is ongoing. Your first context design won't be your best. As you see the agent in production, you'll notice patterns. Queries where it has too little context and struggles. Queries where it has too much irrelevant context and drifts. Treat context engineering as an ongoing practice. Review it when you update the system prompt. Review it when the knowledge base changes. Review it when you see a systematic pattern of errors. In the next lesson, we'll look at how agents remember across interactions. The 3 layers and 4 categories of agent memory. Agents that forget are agents that frustrate. The customer explains their situation. The agent handles it. The customer comes back the next day, and the agent has no idea who they are. That experience destroys the value of an AI agent instantly. Memory is what separates a useful agent from a frustrating one. This lesson gives you a practical framework for building memory that works and understanding the trade-offs in each approach. 3 layers of agent memory. Layer 1, in-context memory. Information held in the current context window. Fast, immediate, and temporary. It disappears when the session ends. Use it for what the agent needs to know right now. This conversation, this task, this session. Layer 2, external memory. Information stored in a database or file and retrieved when needed. Persistent across sessions. Searchable. This is where customer history, preferences, and prior decisions live. Layer 3, model weights. Knowledge baked into the model itself through training or fine-tuning. This is the agent's permanent, unchangeable background knowledge. Slow to update, but always present. 4 categories of memory content. What gets stored in external memory falls into 4 categories. Current task context. Where is this specific interaction up to? What has already been done? Stable preferences. How does this user or system prefer to receive information? What format? What tone? What level of detail? Historical records. What happened in prior interactions? What was resolved? What was escalated? What was promised? Correction history. Where has the agent previously made mistakes for this user or context? And how were they corrected? Correction history is the most valuable category and the most commonly omitted one. When memory goes wrong. Memory systems fail in 2 ways. Too little. The agent doesn't know things it should. Too much. The agent retrieves information that is outdated, incorrect, or no longer relevant. Stale memory is dangerous. A preference recorded 6 months ago may no longer reflect the user's current situation. A promised resolution that was superseded by a second conversation. A correction that was specific to one context being applied to a different one. Build memory with expiry logic. Not all information should be retrieved indefinitely. Some records should be archived after a defined period. Some should trigger a confirmation before being used again. Practical memory architecture. For most production agents, the memory architecture is simpler than it sounds. A database table that stores session summaries, a preferences record updated after each interaction where a preference is expressed, a corrections log that flags specific scenarios where the agent behaved incorrectly. These 3 data stores, connected to a retrieval step at the start of each session, give your agent functional memory without over-engineering. Start simple. Add sophistication as the patterns of use become clear. Memory as a competitive advantage. An agent with good memory doesn't just perform better, it creates a better experience. The customer feels known, the employee feels supported, the process feels intelligent rather than mechanical. Memory is where the agent starts to feel like a colleague rather than a tool. That perception drives adoption. Adoption drives the data. Data drives improvement. It compounds. In the next lesson, we'll look at the tools the agent connects to and what tool use actually means at the architecture level. The agent that can only talk. An agent without tools can only generate text. It can answer questions. It can draft documents. It can synthesize information it already has. But it cannot look anything up. It cannot take any action. It cannot read a live document, check a current price, update a record, or send a message. Tools are what give an agent reach. They transform it from a sophisticated text generator into an autonomous actor. What tool use actually means. When we say an agent uses tools, we mean it can call external functions. Those functions return information or take actions in external systems. At the technical level, it works like this. The agent's system prompt includes a list of available tools. Each tool has a name, a description of what it does, and a specification of what inputs it needs. When the agent decides a tool is needed, it generates a structured call. The orchestration layer executes that call. The result is returned to the agent as context. The agent uses that result to continue its task. The agent doesn't execute code. It decides when to ask for something. The system does the asking. Categories of tools. Tools fall into three categories. Read tools. The agent retrieves information without changing anything. Searching a database, reading a document, looking up a customer record, checking current inventory. These are safe to use freely, no side effects. Write tools. The agent creates or modifies something, updating a CRM field, creating a calendar entry, sending a message, logging a record. These need to be bounded by the reversibility rules from Section 3. Action tools. The agent triggers an external process, calling an API, initiating a workflow, escalating a ticket. These are the highest stakes category and need the tightest controls. API connections in practice. Every tool is an API connection, an agreement between your agent system and an external service about what can be requested and what will be returned. Well-designed API connections have four properties. Specificity. The tool does one thing, described precisely. Schema. The input and output are fully specified, so the agent knows exactly how to call it and what to expect back. Error handling. The tool returns a clear error message when it fails, not silence. Rate limits. The connection enforces usage limits, so a looping agent can't cause an outage. Don't connect tools that don't yet have all four properties. A tool with an ambiguous schema will be called incorrectly. A tool with no error handling will cause the agent to stall silently. Tool design is as important as prompt design. This is the lesson most builders learn the hard way. They spend weeks refining the system prompt and an afternoon on the tools. Then they wonder why the agent behaves inconsistently. The agent's decisions are only as good as the information its tools return. A retrieval tool that surfaces the wrong content. A write tool that accepts inputs in an ambiguous format. An action tool that confirms success even when it failed. Each one shapes agent behavior in ways the prompt cannot correct. Invest in tool quality. Test each tool in isolation before connecting it to the agent. The tools are not accessories. They are the agent's hands. Start with fewer tools. A common mistake is connecting too many tools at once. More tools mean more decisions for the agent to make about which tool to use when. More decision points mean more failure modes. Start with the minimum set of tools required for the core task. Get those tools working reliably. Add new tools one at a time, testing thoroughly after each addition. A well-integrated set of 3 tools outperforms a loosely connected set of 10. In the next lesson, we'll look at how these tools are coordinated, the orchestration design. Who's in charge? An agent with tools, memory, and a system prompt can do a lot of things. The orchestration layer decides when it does each of them, and more importantly, when it stops. Orchestration is the coordination logic that sequences the agent's actions. Without it, you have a capable system with no sense of order. With it, you have a reliable workflow. 2 concepts define good orchestration design: bounded authority, stopping rules. Bounded authority. Bounded authority means the agent can only make a decision within a defined scope. It cannot decide to use a tool it was not given. It cannot decide to skip a required step. It cannot decide to continue past a defined stopping point. This sounds restrictive. It isn't. An agent with clearly bounded authority behaves predictably. A predictable agent can be trusted. A trusted agent gets more autonomy over time. Define the authority boundary for your agent before the build. Not in the prompt, in the orchestration logic. Prompt instructions can be overridden by clever inputs. Orchestration logic cannot. Hard-coded versus soft-coded controls. Orchestration controls fall into two categories: hard-coded, always enforced, regardless of any instruction. The agent cannot call the payment tool without a human approval record in the session. The agent cannot continue after processing more than 500 records without a checkpoint review. These live in the orchestration layer. They are not in the prompt. They cannot be argued out of. Soft-coded, configurable defaults. By default, the agent sends a confirmation before completing a write action. This can be disabled in supervised mode. Soft-coded controls give you operational flexibility while keeping the safe defaults in place. Stopping rules. A stopping rule defines when the agent ends its current task. Not when it fails, when it's done. Good stopping rules are tied to output state, not time. The task is complete when a response has been sent and a ticket has been logged with status resolved. Not, the agent runs for 30 seconds and then stops. Also define stopping rules for failure cases. If the agent has not been able to classify the query after 3 attempts, it stops and escalates. If a required tool returns an error twice in succession, the agent stops the session and alerts the operations team. Stopping rules prevent loops. Without them, agents can enter cycles, retrying, rechecking, regenerating, consuming resources and producing nothing useful. Orchestration in practice. Most orchestration is simpler than it sounds. A sequence of steps. Each step has a defined input, a defined tool or model call, and a defined output. The output of step n is the input of step n+1. Stopping rules define when n+1 doesn't happen. Draw the sequence before you build it. A flowchart on a whiteboard. It should be readable by a non-technical stakeholder. If it isn't, the orchestration is too complex. Simplify it, then build it. The test of good orchestration. A well-designed orchestration passes this test. You can describe every path the agent can take, from trigger to completion, in plain language. You can trace any unexpected output back to a specific step. You can modify one step without breaking others. That's modular, predictable, and debuggable. Those three properties make the difference between an agent you maintain with confidence and one you're afraid to touch. In the next lesson, we'll look at the decision loop, the 5-part cycle that drives every agent's thinking process. How the agent thinks. Between the trigger and the output, the agent runs a loop. It observes, it reasons, it decides, it acts, it evaluates. 5 steps, every time, whether the task takes 2 seconds or 20 minutes. Understanding this loop doesn't make you a developer. It makes you a better designer, because you can anticipate where the loop breaks before it does. Step 1, observe. Step 2, reason. Step 1, observe. The agent reads its current context, the system prompt, the user message, any retrieved memory, any tool results from previous steps. It builds a picture of what is happening and what is known. Step 2, reason. The agent applies its instructions to what it has observed. It identifies what needs to happen next. Which rule applies? Which tool is needed? Is there enough information to proceed? This step is where the quality of the system prompt has the most impact. Clear instructions produce clear reasoning. Vague instructions produce inconsistent reasoning. Step 3, decide. Step 4, act. Step 3, decide. The agent selects a course of action. Continue with a tool call, generate a response, escalate, or stop. The decision is shaped by the orchestration rules you've defined. Bounded authority and stopping rules live here. Step 4, act. The agent executes the decision, calls a tool, writes a response, logs a record. The action produces output that feeds back into step 1 of the next loop iteration. Most agent tasks involve multiple loop cycles. Each cycle builds on the output of the last. Step 5, evaluate. Step 5, evaluate. The agent assesses whether its action achieved the intended result. Did the tool return what was expected? Does the current state match the stopping condition? Is the task complete, or does another loop cycle begin? This evaluation step is where self-correction happens. A well-designed agent that calls a tool and receives an error doesn't freeze. It evaluates the error, applies its rules for that situation, and decides whether to retry, use an alternative path, or escalate. Evaluation is not automatic. It needs to be designed. Define what success looks like at each step, so the agent knows what to compare against. The decision loop design checklist. Before your agent goes to build, validate the loop design against 5 questions. Is the observation step receiving complete, relevant context at each cycle? Are the reasoning instructions specific enough to produce consistent decisions? Is every decision point covered by a rule or example in the system prompt? Does every action have a defined, expected outcome that feeds the evaluation step? Is every evaluation step connected to either a next action or a stopping rule? 5 yes answers, the loop is ready to build. Any no, there's a design gap that will surface as inconsistent behavior in production. The loop is why agent debugging is different. When an agent fails, the failure is usually not at a single point. It propagates. A flawed observation leads to flawed reasoning. Flawed reasoning leads to a flawed decision. A flawed decision leads to an action that makes the next observation even harder to interpret. Understanding the loop lets you trace a failure backward. What was the agent observing when it made the wrong decision? What reasoning led it there? That's the fix. Not the output, not the action, but the step in the loop where the error originated. In the next lesson, we'll close out the 9 components with the layer users actually see, interfaces. The only part your users see. 8 of the 9 components are invisible to the people using your agent. They never see the system prompt. They never see the decision loop. They never see the orchestration rules. They see the interface, how they start an interaction, how the agent responds, how the interaction ends. The interface is where the agent's design becomes the user's experience. Get the interface right and everything else disappears. Get it wrong and nothing else matters. Entry points. How users reach the agent. The entry point is how a user initiates an interaction. There are 4 common types. Chat interface. The user types a message. Familiar, flexible, works for broad conversational tasks. The risk, users can ask anything, which means your scope boundaries get tested from day one. Form or structured input. The user fills in defined fields. More constrained, higher accuracy because the input is predictable. Best for task-specific agents where the query structure is known in advance. API trigger. Another system initiates the agent. No human typing anything. The agent is embedded in a workflow. Fastest and most reliable because the input format is always correct. Event trigger. The agent activates when a condition is met. A new record arrives. A threshold is crossed. A deadline is reached. Fully autonomous initiation. Matching entry point to use case. The entry point you choose shapes the entire agent experience. A chat interface on a data extraction agent creates unnecessary complexity. A form on a conversational support agent creates unnecessary friction. Match the entry point to the nature of the task. If the input is structured and predictable, use a form or API trigger. If the input varies and requires natural language, use a chat interface. If the agent should run without human initiation, use event triggers. Consider the technical environment too. Will this agent be embedded in an existing product, accessed via a standalone page, triggered programmatically by another system? The answer shapes which entry point is even possible. Exit points. How interactions end. Exit points are as important as entry points and far less often designed deliberately. An exit point is the moment the agent's job is complete, from the user's perspective, not from the agent's perspective, from the user's. A support agent that resolves a query has a clear exit point. Your issue has been resolved. Is there anything else I can help you with? A data processing agent has a different exit point, a confirmation record, a logged output, an email notification that the batch is complete. Define the exit point for every user journey your agent supports, not just the happy path. What does the exit look like when the agent escalates? When it fails gracefully? When the user abandons the interaction mid-flow? Designing for graceful failure. Users will always find ways to use your agent that you didn't anticipate. Graceful failure is what happens when the agent meets its limits without humiliating the user or damaging the brand. A graceful failure has 3 qualities. It acknowledges what the agent can't do. It offers an alternative path. It doesn't leave the user stuck. I'm not able to help with that specific query, but I can connect you to a specialist who can, or I can guide you to our help center for more options. That's not a failure. That's a well-designed exit. Test the interface before anything else. Here is a counterintuitive piece of advice. Test the user-facing interface early, before the back-end logic is fully connected, before the tools are all wired up, before the memory system is complete. Put a prototype in front of a real user. Watch what they type. Watch where they get confused. Watch what exit they expect that you haven't designed yet. That information is more valuable than any internal review session. The interface is the agent. From the user's perspective, there is nothing else. Design it like it matters, because it's the only part that does to them. Section 4 is complete. 9 components, 1 coherent system. In Section 5, we'll choose how to build it. You're always building in 3 layers. Every agent, regardless of how it was built or which platform it runs on, consists of 3 layers: the model layer, the orchestration layer, the interface layer. When you choose a build tool, you're choosing how much control you have over each of those layers. That's the real decision, not which platform is best, but which layers do I need to own. This mental model will make every build decision clearer, now, and for every agent you build in the future. Layer 1, the model layer. The model layer is the AI, the reasoning engine, what you're calling when you use GPT, Claude, Gemini, or any other large language model. At this layer, your primary decisions are which model family to use, which specific model within that family, and whether to customize it with fine-tuning or rely entirely on prompting. For most first builds, you're not customizing at this layer. You're choosing a model and writing a good prompt. That's it. Most no-code platforms abstract this layer entirely. They pick the model for you. Code-first frameworks give you full control. Neither is inherently better. It depends on whether the model choice matters to your specific use case. Layer 2, the orchestration layer. The orchestration layer is the logic that coordinates the agent's actions, the decision loop, the tool calls, the memory retrieval, the stopping rules, everything we covered in Section 4. This is the layer where most of the meaningful customization happens, and it's the layer where no-code platforms are most constrained. If your agent needs a straightforward linear workflow, most platforms handle it. If it needs conditional branching, dynamic tool selection, or complex multi-step reasoning, you'll need more control than most no-code tools provide. The honest question: how complex is your orchestration? Simple, medium, or complex? The answer tells you whether a no-code platform will work. Layer 3, the interface layer. The interface layer is what users interact with: chat widget, form, API endpoint, email integration, voice interface. This is often the easiest layer to customize. Most platforms offer interface flexibility even when they constrain the orchestration. The interface layer is also where branding and user experience decisions live. Does the agent need to look like it's part of your existing product? Does it need to match your company's visual identity? Does it need to behave consistently with your support team's tone? Those requirements might push you towards a code-first approach, even if your orchestration is simple. Identifying which layers you need to own. Work through these 3 questions. First, does the model choice matter enough to require direct model access? If no, abstract it. Second, is the orchestration logic complex enough that a visual workflow builder would struggle to represent it? If no, a no-code platform works. Third, does the interface need to be deeply integrated with existing systems or branded experiences? If no, a standard interface is fine. If you answered no to all 3, a no-code platform is your fastest path to value. 1 yes, depending on which layer, moves you towards a hybrid or code-first approach. 2 or 3 yeses, you're in code-first territory. Why this model makes you a better commissioner, even if you'll never write a line of code. This 3-layer model makes you a better commissioner of agent builds. You can ask your technical team, at which layer are we customizing? Why? You can challenge scope creep. Are we building something at the orchestration layer that a no-code tool could handle? You can evaluate vendors. What control do they give me at each layer? That's the vocabulary of informed decision-making. It's the difference between a stakeholder who gets surprised by agent projects and one who shapes them. In the next lesson, we'll walk through the no-code platform specifically, what they do well and where they hit a ceiling. Fast to start. Honest about the ceiling. No-code platforms are genuinely excellent for a specific set of agent use cases. They are also genuinely limited for others. This lesson gives you an honest picture of both. The goal is not to recommend one tool. Tools change faster than this course can keep up. The goal is to give you the framework to evaluate any no-code platform confidently, so you can make the right choice for your context. What no-code platforms are built to do. No-code agent builders are designed for users who want to deploy quickly without writing code. They achieve this by abstracting the model layer, providing visual orchestration builders, and packaging common integrations as pre-built connectors. They excel at standard customer service flows, FAQ and knowledge base agents, simple data retrieval and summarization, email and calendar integrations, internal help desk automation. If your use case fits one of these patterns and your orchestration is linear, a no-code platform can have you live in days, not months. Where no-code platforms hit their ceiling. Complex conditional logic. Multi-agent orchestration, where several agents hand off to each other. Custom tool integration beyond the platform's pre-built connector library. High-volume production with strict performance and cost requirements. Enterprise compliance requirements that demand audit trails the platform wasn't designed to produce. These are not edge cases. For many organizations, one or more of these requirements applies from the start. Know them before you commit to a platform, not after 6 months of trying to work around the limitations. Evaluating a no-code platform. 5 questions. What models can I access, and can I switch between them? What integrations are pre-built, and what do custom integrations require? What does the orchestration builder actually support? Linear only or conditional logic? What are the rate limits, latency guarantees, and pricing structure at production scale? What data does the platform store and where? The last question matters most for enterprise use cases. If the platform logs your users' messages on its own servers, that's a data governance conversation before it's a technology conversation. The vendor lock in consideration number. Code platforms create dependency. The system prompt lives in their environment. The integrations run through their infrastructure. The data is stored in their system. Switching platforms is not a copy-paste exercise. It's a rebuild. That's not a reason to avoid no-code platforms. It's a reason to be intentional about choosing one. Evaluate the platform's track record, financial stability, and pricing trajectory. A platform that doubles its pricing after you've built 3 agents on it is a significant business risk. The right first question. The right first question for any no-code platform evaluation is not, what features does it have? It's, can this platform do exactly what my highest priority use case requires? Build a requirements list from your agent brief. Match it against the platform's documented capabilities. If more than 20% of your requirements require workarounds, the platform isn't the right fit. Move to a code-first framework instead. In the next lesson, we'll look at the code-first options, what they offer and what they demand in return. More power, more responsibility. Code-first frameworks give you full control over all 3 layers of the agent stack: the model, the orchestration, the interface. Nothing is abstracted away. Everything is customizable. That power comes with a cost. Time to build, technical expertise to maintain, ongoing responsibility for infrastructure, reliability, and security. Code-first is not harder. It's a different trade-off. And for many use cases, it's the right one. What code-first frameworks provide? Code-first frameworks are software libraries that handle the low-level complexity of agent development. Model API calls, memory management, tool registration and execution, conversation history management, multi-agent coordination. They give developers a structured way to build agent systems without starting from scratch each time. Think of them as building materials with instructions, not pre-built houses. You still build the house, but you don't have to manufacture the bricks. What code curious first demands development skill? Someone on your team needs to be able to read, write, and debug code in the language the framework uses. Most major frameworks use Python. Some use JavaScript. A few are language agnostic. If you don't have this skill in-house, you need a developer or a technical agency. That changes your project economics. Infrastructure responsibility. A code-first agent runs somewhere. A server, a cloud function, a container. You are responsible for its availability, its scaling, and its security. That's not prohibitive, but it needs to be in the plan. Testing and maintenance. You own the test suite. You own the updates when the underlying model API changes. You own the debugging when something breaks. These costs are real and ongoing. When code first is the right choice, your orchestration logic is too complex for a visual builder. You need to integrate with systems the no-code platforms don't support. You have strict data governance requirements that prevent data from leaving your infrastructure. You're building an agent that will process high volumes, and cost control at token level is critical. You're building a product that will be sold to others, and you need to own the full stack. Any one of these is a sufficient reason to choose code first. Two or more, and the choice is clear. The build team you need: a minimal code, first team for a first agent build. One developer who knows the framework. One person who owns the domain knowledge and the prompt design. One stakeholder who owns the business requirements and signs off on the output quality. That's 3 people. It doesn't need to be a large team. It needs to be a focused team. One person trying to do all 3 roles will produce an agent that technically works, but doesn't solve the business problem. The domain knowledge and the technical execution need to be distinct. The hybrid path. Most mature agent deployments end up hybrid. A no-code platform handles the standard use cases. A code-first component handles the edge cases or the high-complexity workflows. The 2 systems talk to each other through APIs. Start where your use case sits. If it's in no-code territory, start there. If the ceiling of no-code is reached, the code-first component is added incrementally. You don't need to choose the final architecture on day one. You need to choose the right starting point. In the next lesson, we'll give you a structured framework for making that starting point decision, the build versus configure matrix. Build or configure? This is the decision that sets your timeline. Build versus configure is the foundational decision that determines your project timeline, your team requirements, and your total cost of ownership. Get it right, and you're live in weeks with a system you can maintain. Get it wrong, and you spend months building something that could have been configured, or configuring something that needed to be built. This lesson gives you a decision matrix, not a vague framework, a scored tool you can apply to your specific use case. What configure means using a platform's existing capabilities, selecting options, connecting integrations, writing prompts without writing custom code. You're working within the platform's design, using the orchestration it provides, connecting the tools it supports, formatting output in the patterns it allows. Configuration is fast. A competent non-developer can configure a capable agent in days. But configuration is bounded. You can only do what the platform was designed to allow. What build means writing code, custom orchestration logic, custom tool integrations, custom memory systems, custom interfaces. You are creating something new, not selecting from a menu. Building is slower. It requires more skill and more ongoing maintenance, but it has no ceiling. If a requirement can be technically implemented, it can be built. The platform's limitations don't apply because there is no platform. There's just a system you own. The decision matrix. Score your use case against 6 factors, 1 to 5 on each. Orchestration complexity. How many conditional branches, loops, and multi-step sequences does the workflow require? Integration specificity. Are your required integrations available as pre-built connectors, or do they require custom API work? Volume and performance. What are the transaction volumes and latency requirements at production scale? Data governance. Can your data live on a third-party platform, or must it remain in your infrastructure? Maintenance resource. Do you have ongoing developer resource to maintain a code-first system? Time to first deployment. Is speed to launch a critical factor, or do you have runway for a longer build? A total score under 15, configure. Between 15 and 22, hybrid. Above 22, build. The factors that override the score. Certain factors override the matrix entirely. If data governance requires your data never leaves your infrastructure, build regardless of the score. If your first deployment date is in 4 weeks, configure regardless of the score. If the only person who could maintain a code-first build has just left the organization, configure and plan the rebuild when the resource is in place. The matrix guides the decision. Hard constraints override it. Identify your hard constraints before you score. Make the decision once, revisit it later. The build versus configure decision is not permanent. A use case that starts on a no-code platform can migrate to a code-first architecture when the business requirements grow beyond the platform's limits. The migration is not free, but it is possible, and it is planned for if the decision is made consciously. Document your decision and the reasoning behind it. In 6 months, when requirements change, the person reviewing the decision needs to understand why it was made, not just what was chosen. In the next lesson, we'll look at what happens when things go wrong, the diagnostic map for the most common failure modes at each layer of the stack. Something will go wrong. Here's where to look. No agent build is without failures. The question is not whether something will break. The question is how quickly you find it and at which layer. Most teams spend hours debugging at the wrong layer. They change the prompt when the problem is in the tools. They rewire the orchestration when the problem is in the model choice. They switch platforms when the problem is in the system prompt. The diagnostic map stops that waste. Layer 1 failures, the model. Symptoms of a model. Layer failure. The agent produces outputs that are factually incorrect in consistent patterns. The agent performs well on simple inputs, but fails systematically on complex ones. The agent ignores instructions it was clearly given. Likely causes: wrong model class for the task. A standard model being used for a task that needs a reasoning model. Model is being asked to hold more context than its window supports. The model has a known limitation for this specific task type. Diagnostic: swap the model. Run the same input through a different model or a different tier. If the output improves significantly, the problem is model selection, not prompt design. Layer 2 failures, the orchestration. Curious. Symptoms: the agent skips steps. The agent repeats steps it already completed. The agent takes an action at the wrong point in the workflow. The agent stalls and doesn't produce output. Likely causes: a stopping rule that is triggering too early or too late. A tool call returning a result in a format the agent doesn't know how to use. A loop that has no exit condition. Diagnostic: trace the decision loop step by step. Which step did the agent complete correctly? Where did it deviate? The deviation point is the failure point. Layer 3 failures, the interface. Symptoms: users abandon the agent before completing their task. The agent receives inputs it wasn't designed to handle. The output format doesn't match what the downstream system expects. Users report that the agent doesn't understand their queries. Likely causes: the entry point doesn't match the way users naturally phrase the task. The output format is correct by the agent's rules, but unreadable in the receiving system. The interface doesn't provide enough guidance for users to give the agent what it needs. Diagnostic: watch real users interact with the agent, not a colleague familiar with the system, a new user encountering it for the first time. You'll see the interface failures within 5 minutes. Cross-layer failures. Some failures look like one layer but originate in another. An interface failure looks like an orchestration failure because the malformed input cascades through the workflow. An orchestration failure looks like a model failure because the agent is making the right decision from a flawed set of tool results. A model failure looks like a prompt failure because the model is interpreting instructions correctly for a different context than the one it's operating in. The diagnostic principle for cross-layer failures. Start from the output and trace backward. What was the last correct output in the sequence? What changed between that output and the first incorrect one? That change in input, context, tool result, or step sequence is your failure point. Build the map before you need it. The diagnostic map is most useful before the first failure, not during it. Before your agent goes live, run through the symptoms at each layer. For each, what would you look at first? Who would you call? How would you reproduce the failure in a test environment? 10 minutes of planning now saves hours of crisis debugging later. Failures in production happen under pressure. Teams that have a diagnostic plan use it calmly. Teams that don't have a plan guess. Guessing is expensive. Section 5 complete. You have a build pathway and a failure plan. In Section 6, we add a different kind of agent entirely. Voice. Same technology, completely different design. Voice agents and text agents share the same underlying models. the same reasoning engine, often the same knowledge base, but they are not the same design problem. The experience of interacting with a voice agent is fundamentally different from the experience of reading a chat response. Different tolerance for latency, different structure for turns, different expectations when things go wrong. Designing for one and deploying to the other is how voice agent projects fail. This lesson explains why voice is a different design and sets up the principles that make voice agents work. The core difference: the ear cannot reread. In a text interface, users can reread a response, scroll back, refer to an earlier message, take their time. The interface is patient. In a voice interface, everything the agent says exists only in the moment it is said. If the user doesn't understand, they have to ask for clarification. If the response is too long, they've missed the important part by the time it arrives. If the pacing is wrong, the experience feels like being lectured, or worse, like talking to a machine. Every design decision in a voice agent flows from this single fact. The ear cannot reread. Design accordingly. What voice changes about response design? Response length shorter. A 3-sentence answer in voice feels longer than a 3-paragraph answer in text. Aim for 1 or 2 sentences per turn. If more is needed, break it into a conversational sequence with questions. Response structure simpler. Text responses can use formatting, headers, and lists. Voice can use none of those. Information must be delivered as narrative or as prompted choice. I can help you with billing, account changes, or technical support. Which do you need? Confirmation patterns, more frequent. Voice users can't scan back to verify what was said. If the agent has understood something that matters, confirm it out loud before acting on it. Just to confirm, you'd like to update the billing address to the one you just gave me. Is that right? Latency, the invisible design constraint. In text, a 2-second response time is fast. In voice, a 2-second pause is awkward. 4 seconds is alarming. Users interpret silence as disconnection or failure. They hang up, they interrupt, they assume something went wrong. Designing for voice means designing for low latency or designing around it. For tasks where a fast response is achievable, voice works. For tasks that require complex retrieval, long-running tool calls, or multi-step reasoning, voice creates a frustrating wait. Either optimize the latency or reconsider the use case for voice. Error recovery in voice text agents that fail gracefully can display a clear error message. Voice agents that fail gracefully need to do something much harder. They need to sound like they're in control even when they're not. A voice error message that sounds robotic or confused destroys trust immediately. Design your voice error recovery as a script. 3 scenarios. The agent didn't understand, the agent understood but can't help, and the agent needs to transfer to a human. For each, write the exact words the agent will say. Test them spoken aloud. They must sound natural. If they don't, rewrite them. Voice requires a different test protocol. Testing a voice agent with your eyes is not enough. You must test it with your ears. Call it, listen to it. Have someone unfamiliar with the project call it and describe their experience. Specifically listen for pauses that feel too long, responses that feel too complex, confirmation prompts that feel condescending, and error recoveries that feel robotic. Any of those is a design failure, even if the underlying logic is correct. In the next lesson, we'll go into the specific design differences that separate effective voice agents from poor ones. 7 design differences that change everything. If you build a voice agent using the same design principles as a text agent, it will be technically functional and experientially poor. The failure won't be dramatic, it will be quiet. Users will find the experience frustrating and slightly off. They won't know why, but they'll stop using it. This lesson gives you the 7 design differences that separate voice agents that work from those that merely operate. Difference 1, turn structure. Difference 2, interruption handling. Turn structure in text, a user message, an agent response, a user message, and so on. Turn structure in voice, messier. Users pause mid-sentence, they trail off, they change direction. The agent needs to know when the user has finished, and that isn't always obvious. Design for natural pause detection. A turn isn't over just because the user stopped speaking for a second. It's over when the pause is long enough to signal completion. That threshold needs to be tuned for your specific use case and user population. Interruption handling. In voice, users interrupt. In text, they can't. Your voice agent needs to handle being interrupted mid-response gracefully. Stop, listen, acknowledge the interruption, respond to what was actually said. An agent that plows through its script after being interrupted feels death. Difference 3, confirmation. Difference 4, escalation. Confirmations are non-negotiable in voice. Before any significant action, the agent confirms what it understood and what it plans to do. You'd like to cancel your subscription, effective at the end of this billing period. Is that correct before I proceed? The confirmation serves two functions. It verifies the agent understood correctly, and it gives the user a clear moment to stop the action before it happens. In voice, users can't undo a confirmed action as easily as they can in a chat interface. The confirmation is the protection. Escalation to a human must be seamless. In text, transferring to a live agent involves a visible handover. In voice, a poor transfer means the user repeats their entire problem. The agent must pass a structured context summary to the human agent, so the call continues from where it left off, not from the beginning. Difference 5, response length. Difference 6, formatting. Response length has already been mentioned, but it's worth repeating because it's the rule most voice agent designs violate. Keep responses to 2 sentences maximum per turn. If you need to convey more, break it across multiple turns using questions as bridges. Your account shows 3 recent transactions. Would you like me to go through them one by one? Formatting in text. Headers, lists, bold text, hyperlinks. Formatting in voice. None of those are possible. Lists become verbal sequences. You have 3 options. Option 1 is emphasis becomes vocal, pausing before key information, repeating important numbers, spelling out anything that could be misheard. Design your voice responses as spoken sentences, not written paragraphs. Read every response aloud before finalizing it. If it doesn't sound natural spoken, rewrite it. Difference 7, persona and tone. Text agents can be slightly formal without feeling cold. Voice agents cannot. The human voice expectation is different. Users are more sensitive to robotic phrasing, awkward pauses, and unnatural sentence structure when they're hearing it than when they're reading it. The voice persona needs to be defined at the word level, not just warm and professional. Specific word choices, specific sentence rhythms, a defined way of handling small talk and pleasantries, a defined response to expressions of frustration. Test the persona as a performance. Have someone read the agent's responses aloud. Do they sound like a person? Do they sound like a good version of a person? If not, the persona needs work before the technology does. Apply these differences before you choose technology. These 7 differences are design requirements. They exist regardless of which technology platform you use to build the voice agent. Understand them first, then choose the technology that makes implementing them possible. A voice agent built on strong design principles with average technology will outperform a voice agent built on excellent technology with weak design. Every time. The design is the product. The technology is the delivery mechanism. In the final lesson of this section, we'll look at where voice agents deliver the most value and which use cases they genuinely shouldn't be used for. Voice wins where text cannot follow. Voice agents are not a premium version of text agents. They are a different tool suited to specific contexts where voice is the natural or only interaction mode. Deploying a voice agent where text would serve better doesn't create a better experience. It creates an expensive one. This lesson maps voice to the use cases where it genuinely outperforms text and names the contexts where it doesn't, so you can make the right call. High-value context 1. Inbound customer calls. The highest value application of voice agents is handling inbound customer calls at scale. The economics are compelling. Staffing a phone line for consistent coverage is expensive. Training agents to handle volume spikes is expensive. Maintaining quality across hundreds of calls a day is difficult. An AI voice agent handles all 3. It's available around the clock. It scales instantly. And with good design, it delivers a consistent experience regardless of volume. For organizations that receive large volumes of structured inbound calls, account queries, appointment booking, order tracking, basic troubleshooting, the voice agent ROI is often the fastest to demonstrate of any agent type. High value context 2, field worker support. Field workers, engineers, technicians, delivery staff, healthcare workers in clinical settings often can't stop and type. Their hands are occupied, their environment is noisy, their need is immediate. They need information right now, spoken to them. A voice agent that can retrieve a technical specification, look up a patient record, or confirm a delivery address on verbal request solves a problem that text agents genuinely can't. This is a category where voice isn't a preference, it's a functional requirement. The design challenge here is the operational environment, noise, interruptions, the need for very short responses. Engineer the agent for the context, not for a quiet office. High-value context 3, accessibility-first products. For users with visual impairments, motor difficulties, or low digital literacy, voice is not a convenience. It is the primary accessible interface. Designing an agent that works well in voice expands your product's reach to users for whom a chat interface would be a significant barrier. This is increasingly a regulatory consideration as well as a human one. Accessibility standards are strengthening in most major markets. A voice-capable agent is a meaningful step towards compliance in contexts where communication with customers is a core business function. Where voice doesn't deliver value. Complex information that requires review. If the user needs to refer back, compare, or study the response, voice fails them. A mortgage comparison, a detailed technical specification, a legal summary. These need text. High-stakes decisions that require confirmation in writing. A voice agent can assist with the conversation leading up to a commitment. The commitment itself should be confirmed in writing. Voice is not the right channel for the final confirmation of anything consequential. Tasks where the input is structured and digital. If the user needs to enter an account number, a date, a reference code, a form is faster and more accurate than voice. Voice adds no value when the input is already structured. Making the voice decision. 3 questions. Is voice the natural or only mode of interaction for this use case? Can the agent's responses be designed to be useful when heard rather than read? Is the latency achievable within the tolerance of the use case? 3 yes answers. Voice is appropriate. 1 no. Reconsider. The best voice agents don't exist because voice is modern or impressive. They exist because voice was the right answer to a specific problem. Section 6 complete. In Section 7, we'll look at the vendor evaluation process, how to assess the platforms and providers you'll rely on to make all of this work. The vendor relationship will outlast the build. Choosing an AI vendor is not like choosing a software subscription. It's closer to choosing a business partner. The model you rely on shapes what your agent can do. The vendor's pricing determines your economics. Their reliability affects your customers. Their data practices affect your compliance. Most organizations choose a vendor because a developer liked the API, or because the sales demo was impressive, or because a competitor is using it. None of those are evaluation criteria. This lesson gives you a structured scorecard for evaluating AI vendors. So the choice is made on evidence, not enthusiasm. Capability. Does it do what you need? The first evaluation dimension is capability. Not is it impressive, but can it do the specific tasks my agent requires? Test the vendor's model against your actual use case, not a demo they provide. Your prompts, your data, your edge cases. Measure the output quality against your success criteria from the agent brief. A vendor who scores well on generic benchmarks but poorly on your specific task is not the right choice. Also evaluate, does the vendor provide the model features your design requires? Tool use, long context windows, fine-tuning, multimodal inputs. If your design needs a feature and the vendor doesn't offer it, capability fails. Reliability and performance. Reliability means the service is available when your agent needs it. Check the vendor's uptime history, not just the advertised SLA, the actual incident history. How often do outages occur? How long do they last? How quickly are they communicated? Performance means the service is fast enough for your use case. Latency at the API level, not in a demo, at the volume you'll be running in production. Request the vendor's P95 latency figures, the response time they hit 95% of the time. If they can't provide it, that's an answer. For voice agents, latency is a hard requirement. For batch processing agents, availability windows may matter more than speed. Match your reliability requirements to your specific use case, not to a general enterprise standard. Security posture and data practices. Two questions that must be answered before any vendor is shortlisted. Where does my data go? Who can see it? Specifically, are your prompts and completions used to train future models? Can the vendor's staff access your production data? Where is data stored geographically? What certifications does the vendor hold? SOC 2, ISO 27001, GDPR compliance. For healthcare, finance, or legal use cases, the compliance requirements are more specific still. Get the answers in writing before you commit. A vendor who answers these questions confidently and completely is demonstrating security maturity. One who deflects, hedges, or offers to follow up is not. Pricing model and lock-in risk. AI vendor pricing is complex. Token-based pricing, flat subscriptions, usage tiers, enterprise contracts with minimums. Run the economics at 3 scales: your launch volume, your 6-month projected volume, and your 12-month projected volume. If the pricing doesn't work at scale, the vendor doesn't work at scale. Lock-in risk is the cost of switching. How much of your system is specific to this vendor's API format? How portable is your system prompt if you move to a different model provider? How many of the integrations you've built depend on vendor-specific features? The higher the lock-in, the more important it is to get the initial vendor decision right. Support and the roadmap. You will need help. A model update breaks your agent's behavior. A rate limit change affects your production volume. A new compliance requirement changes what data you can send to the API. The question is, what kind of support can you get and how quickly? Evaluate the vendor's support tier for your contract level. Response time commitments, access to technical account management, communication channels for incidents. Then evaluate the roadmap. Is the vendor investing in the features that will matter to you in 12 months? A vendor that is moving away from your use case is not a partner, it's a liability. In the next lesson, we'll decode the terminology you'll encounter in every vendor conversation. The jargon that shapes every vendor conversation. AI vendor conversations are full of technical terminology. Context windows, RAG, fine-tuning, token costs, rate limits. Each term sounds specific. Each one means something that directly affects your build decisions and your economics. This lesson decodes the terms you'll encounter most often. Not to make you a technical expert, to make you an informed commissioner. Knowing what these terms mean lets you ask the right questions and recognize when the answers don't add up. Context window and token costs. Context window, the amount of text the model can hold in its working memory at once. Measured in tokens, roughly 3/4 of a word each. A 128,000 token context window can hold approximately 90,000 words at once. That's a substantial document, a long conversation history, and a detailed system prompt simultaneously. Why it matters. Tasks that require the agent to reference long documents, maintain long conversations, or hold multiple sources simultaneously need large context windows. A model with a smaller context window will either truncate information or require you to engineer around the limitation. Token costs. You pay per token processed, for both the input sent to the model and the output it generates. Input tokens and output tokens are typically priced differently. Model output is usually more expensive than input. Your cost per interaction is a function of your average context size plus your average response length. Model that. RAG and fine-tuning. RAG, Retrieval Augmented Generation, a technique for giving the model access to a specific knowledge base at query time. Instead of training the knowledge into the model, you retrieve relevant sections from a document store and inject them into the context at runtime. The model answers from what was retrieved, not from general training. RAG is the right approach for most business knowledge bases. Policies, product documentation, FAQs, internal procedures. It's faster to update than fine-tuning and doesn't risk the knowledge being mixed with unrelated training data. Fine-tuning, adjusting the model's weights using examples from your specific domain, makes the model behave differently by default, not just for a single interaction. Useful when you need consistent tone, formatting, or domain-specific reasoning that prompting alone doesn't achieve. More expensive and slower to update than RAG. Most first builds don't need it. Latency, rate limits, and SLAs. Latency, the time between sending a request to the model and receiving a response, measured in milliseconds or seconds, varies by model size, server load, and request complexity. For interactive use cases, a user waiting for a response, your latency target is typically under 2 seconds. For batch processing, latency matters less than throughput. Rate limits, the maximum number of API requests or tokens you can process in a given time period. Most vendors apply rate limits per account or per tier. Hitting a rate limit means your requests queue or fail. At production scale, rate limits can become a bottleneck. Understand your limits before you launch and negotiate them if your projected volume requires it. SLAs, service level agreements, the vendor's contractual commitment on uptime and response time. 99.9% uptime sounds high. It means 8.7 hours of downtime per year.
For a customer-facing agent that runs 24/7, that's worth understanding.
Prompt caching and embeddings. Prompt caching, a feature that allows the vendor to store and reuse the processed version of a prompt, reducing cost and latency for repeated requests with the same system prompt. For agents with long, static system prompts, this can meaningfully reduce your per interaction cost. Ask whether the vendor offers it and how it works with your architecture. Embeddings, a technique for representing text as a numerical vector that captures its meaning. Embeddings are the foundation of RAG search. You convert your knowledge-based documents into embeddings. When a user query arrives, you convert the query to an embedding and find the most semantically similar documents. That's how RAG retrieves the right content. Understanding embeddings helps you understand why RAG retrieval quality varies and how to improve it. Use the terminology to ask better questions. You don't need to be an engineer to use this vocabulary. You need to be informed enough to ask questions that get specific answers. What is your P95 latency at 1,000 requests per minute? Do you offer prompt caching, and what is the cost reduction? What are our rate limits at the enterprise tier, and how do we request an increase? Is our data used to train future models, and where is that governed in the contract? Vendors who can answer these questions precisely are vendors who understand their own product. Vendors who can't are vendors who won't be reliable partners. In the next lesson, we'll build on this vocabulary to design a proof of concept that generates real decision data. A demo is not a proof of concept. Every AI vendor can show you a compelling demo. Curated inputs, best case outputs, ideal conditions. A demo proves the technology is capable. It proves nothing about whether it works for your use case. A proof of concept is different. It's a structured test against your actual requirements, your data, your edge cases, your success criteria. The output is a go, no-go decision, not an impression. This lesson gives you a 2-week POC design that generates the data you need to make that decision. What are good POC tests? A good POC tests 3 things. Core capability. Can the system do the primary task at the required quality level? Edge case performance. How does the system behave when the input is ambiguous, incomplete, or out of scope? Operational fit. Does the system integrate with your technical environment, meet your latency requirements, and comply with your data governance standards? These 3 dimensions give you a complete picture. A system that passes core capability but fails on edge cases will generate complaints in production. A system that passes both but fails on operational fit can't be deployed. You need all 3. Week 1. Build the test environment. Day 1 to 2. Define your test cases. 30 cases minimum. 10 core happy path scenarios. 10 edge cases. Ambiguous inputs. Incomplete information. Queries at the boundary of scope. 10 adversarial cases. Inputs that test the agent's constraints and boundaries. Day 3 to 4. Prepare your test data. Real examples where possible, anonymized appropriately. Each test case should have a defined expected output so you can score the result. Not the agent said something useful, the agent correctly classified the query as billing related and provided the policy reference number. Day 5. Set up the test environment. Get the vendor's API connected. Run a small batch to confirm the environment is working. Don't start formal testing until you're confident the infrastructure is stable. Week 2. Run and score focused. Days 6 to 8. Run the full test suite. Review every output. Score each one against your expected output. Binary, pass-fail for factual correctness. A 5-point scale for quality dimensions like tone, format, and completeness. Days 9 to 10. Analyze the results. Where did the system fail? Is there a pattern, a category of query, a type of input, a boundary condition? A system that fails randomly is less concerning than one that fails systematically. Systematic failure points to a design problem. Random failure points to variability in the model, which can be managed. Final 2 days. Write the POC report. Core capability score, edge case performance, operational fit findings, total cost projection at production volume. Recommendation: proceed with modifications, or do not proceed. Running POCs with multiple vendors. If you're choosing between vendors, run the same POC against each. Same test cases, same scoring criteria, same evaluation criteria. The only variable is the vendor. That's a controlled comparison, not a beauty contest. The scoring will rarely be clean. Vendor A may outperform on core capability, but underperform on latency. Vendor B may be cheaper, but have a data governance gap. The POC makes those trade-offs explicit and quantified. The decision then belongs to the people who understand the business priorities. What the POC doesn't prove. A successful POC proves the system can work for your use case. It does not prove the system will work at production scale. It does not prove the vendor will maintain quality as their platform evolves. And it does not prove the system will continue to work if your data or process changes. Plan for reevaluation at 6 months. The POC is the start of an evidence-based vendor relationship, not the end of the evaluation process. The best vendor relationships are ones where you're continuously generating data about whether the choice is still the right one. Section 7 complete. In Section 8, we build it. The order matters more than you think. Most agent builds fail, not because of what gets built, but because of the order it gets built in. Teams start with the interface because it's visible, or with the tools because they're exciting, or with the memory system because someone read an article about it. And then they spend weeks trying to make these components work with a system prompt that was written in an afternoon. The right build order flows from the design principles we've established. Start with the logic core, build outward. Never build an interface before you know the core works. Step 1, the system prompt. The system prompt comes first, always, without exception. Every other component depends on it. The tools are called based on rules in the prompt. The memory is retrieved in response to goals defined in the prompt. The orchestration sequences are governed by logic described in the prompt. If the prompt is weak, everything built on top of it is weak. Spend more time on the system prompt than you think is necessary. Write it. Test it manually against sample inputs. Refine it. Test again. Only when you can accurately predict how the agent will respond to your test inputs does the prompt move to the next stage. Step 2. Tools. Step 3. Memory. Tools come second. Build each tool in isolation before connecting it to the agent. Test each connection individually. Confirm the input schema works. Confirm the output format is what the agent expects. Confirm error handling returns something useful. Only then integrate. Memory comes third. Test first without memory. Understand the base behavior of the agent on fresh inputs. Then add memory and test again. The difference between the two test sets tells you whether memory is helping or creating unexpected behavior. Memory that makes the agent less predictable needs redesign before it goes to production. Step 4, orchestration. Step 5, interface. Orchestration comes fourth. At this point, you have a working prompt, connected tools, and tested memory. Now you sequence them. Build the simplest version of the orchestration first. Linear, no branching. Test it end to end. Then add conditional logic one branch at a time. Each addition gets tested before the next is added. Interface comes last. The interface is the presentation layer on a working system. If the system underneath isn't working, the interface cannot fix it. Building the interface first is putting a facade on a building that hasn't been structurally completed. It hides problems and delays the discovery of failures that become much harder to fix once users have expectations. The temptation to skip steps. There will be pressure to skip steps. A deadline will make the interface seem urgent. A stakeholder will want to see a demo before the tools are tested. A developer will connect the memory before the prompt is stable. Every skip step creates technical debt. Debt that gets collected in production, usually at the worst possible time. A tool failure that looks like a prompt problem. A memory issue that looks like an orchestration bug. Because the build order was reversed, the root cause is hidden under layers of later work. Hold the build order. It's not perfectionism, it's risk management. The build order and your timeline. Knowing the build order lets you plan the timeline realistically. The system prompt requires at least 3 iterative cycles of write, test, refine. Each tool integration requires standalone testing before agent integration. Memory requires a comparison test, with and without. Orchestration requires incremental testing after each branch addition. Build that sequencing into your project plan. A first agent build typically takes 4 to 8 weeks done well. Done in a rush, without respecting the build order, it takes 4 to 8 weeks plus 3 months of production firefighting. In the next lesson, we'll look at what makes testing an agent different from testing any other software. The test you run on an agent is not a standard software test. In traditional software testing, the goal is to confirm that given input A, the system always produces output B. Deterministic, repeatable, verifiable. Agents are not deterministic. Given input A, an agent might produce output B prime, or output B with different wording, different structure, and, occasionally, a different conclusion. Testing an agent means evaluating a probabilistic system. The test methodology has to match. This lesson gives you the principles that govern agent testing, so your test results are meaningful, not misleading. The core difference: evaluating quality, not correctness. In software testing, an output is correct or it isn't. The function returned the right value or it didn't. Binary, easy to automate. In agent testing, most outputs require quality evaluation. Is this response accurate? Is it complete? Is it appropriately scoped? Is the tone right? Is the format correct? These are judgment calls, and judgment calls don't automate easily. Your testing process needs to account for human evaluation, not for every test case, but for a representative sample evaluated by someone who understands the standard. That evaluation produces the data you need to make release decisions. What agents need that software doesn't. Adversarial testing. Software testing checks that the system does what it's supposed to do. Agent testing also checks that the system doesn't do what it's not supposed to do. That's a different type of test, and most teams skip it. Adversarial testing means deliberately trying to break the agent's scope boundaries. Give it an input that's close to in scope, but isn't. Give it an instruction that conflicts with its constraints. Give it a prompt that appears to override its system configuration. These are exactly the inputs real users will generate, often without any malicious intent. An agent that fails on adversarial inputs in testing fails on them in production too. The regression problem software changes are tested against a regression suite to confirm nothing that worked previously has broken. Agent testing faces a more complex version of this problem. When you update a system prompt, a tool, or the underlying model, the agent's behavior can change in ways that aren't immediately visible. A prompt change that improves performance on customer queries might degrade performance on escalation handling. A model update from the vendor might change how the agent interprets ambiguous instructions. For this reason, maintain a fixed set of test inputs that you run against every significant change. The same 30 test cases from the POC. Track the score across changes. Any score regression on previously passing cases is a flag, regardless of whether the new change appears to be unrelated. Automated testing for agents. Not all agent testing requires human evaluation. Output format testing can be automated. If the agent should always return a structured JSON object, that can be verified programmatically. If the agent should always include a specific field, that can be checked. If response length must be under a defined limit, that can be measured. Build automated checks for the structural properties of the output. Reserve human evaluation for the quality properties. This gives you a scalable testing pipeline that catches structural failures automatically while maintaining meaningful quality assessment. Testing is not a phase, it's a practice. The biggest testing mistake in agent builds is treating testing as a phase that happens before launch. Test before launch, test at launch, test in production, test after every significant change, test quarterly even when nothing has changed, because the model, the data, and the user population all shift over time. Agents that aren't continuously tested are agents that degrade silently. The output quality drifts. Nobody notices until a user complains. By that point, the drift has been happening for weeks. Build testing into the operational rhythm, not the project plan. In the next lesson, we'll build your specific test suite, from structure to scoring criteria. From principles to practice, your test suite. The previous lesson explained why agent testing is different from software testing. This lesson builds your test suite, not in theory, a practical structure you can apply to your agent before it goes live. A complete test suite has 4 layers: golden path tests, edge case tests, adversarial tests, and failure mode tests. Each layer tests something the others don't. Layer 1, golden path tests. Golden path tests confirm the agent handles its core task correctly under ideal conditions. Well-formed inputs, all required information present, no ambiguity, no unusual circumstances. Build 10 to 15 golden path tests. Cover each of the main input types your agent will receive. For each, write the input, define the ideal output, and specify the criteria for evaluating whether the actual output matches. Correctly identifies the query category and provides the relevant policy reference and maintains the defined tone. 3 criteria, all must pass. Golden path tests are your baseline. If the agent fails these, stop. Something fundamental is wrong with the core design before you test anything more complex. Layer 2, edge case tests. Edge cases are inputs that sit at the boundary of what the agent is designed to handle. Ambiguous queries that could be interpreted multiple ways. Queries that are related to but outside the agent's defined scope. Inputs that are incomplete or poorly formed. Queries in an unexpected format. Very short, very long, in an unexpected structure. Build 10 to 15 edge case tests. For each, what is the ideal behavior? Does the agent ask for clarification? Does it handle the most reasonable interpretation? Does it recognize the query is out of scope and escalate appropriately? Edge cases are where the system prompt earns its keep. If the prompt is well written, most edge cases resolve correctly. Layer 3, adversarial tests. Layer 4, failure mode tests. Adversarial tests check whether the agent can be pushed outside its defined boundaries. Inputs that attempt to override the system prompt. Requests for information the agent is explicitly prohibited from sharing. Instructions that conflict with the agent's constraints. Scenarios that try to get the agent to take an irreversible action without the required approval step. The agent should handle all of these within its defined boundaries. If it doesn't, the boundaries aren't robust enough. Failure mode tests check graceful degradation. What happens when a required tool returns an error? When a database query returns no results? When the input is in a language the agent wasn't designed for? When the session runs unusually long? Failure mode tests ensure the agent fails safely, not silently and not catastrophically. Scoring your test suite. For each test case, record 3 things: the actual output produced, whether it passed your defined criteria, pass or fail, and your quality score on a 1 to 5 scale for the dimensions that apply: accuracy, completeness, tone, format. Set a launch threshold before testing begins. Something like 90% pass rate on golden path tests, 80% pass rate on edge cases, 100% pass rate on adversarial tests. The thresholds reflect the stakes. An adversarial failure is a boundary violation. 100% pass rate is not optional. An edge case failure is a quality issue. The threshold can reflect your launch tolerance for imperfect edge case handling. What to do with the results. Test results are diagnostic data, not a pass-fail verdict on the project. A pattern of failures in edge cases points to the system prompt. Failures in adversarial tests point to the constraint definitions. Failures in failure mode tests point to the orchestration logic. Each failure category has a corresponding fix. Run the test suite, diagnose the failures, fix the source, retest. Don't launch until the thresholds are met. The 2 or 3 days of additional iteration will save you weeks of production firefighting. In the next lesson, we'll go deeper on 4 specific failure patterns and how to diagnose them precisely. 4 patterns. Every production failure fits one. When an agent fails in production, the failure looks unique. A specific query, a specific output, a specific user complaint. But underneath the surface, almost every production failure is one of 4 patterns: hallucination, loop stall, scope escape, tool misuse. Learn to recognize each one on site and you'll diagnose failures in minutes. Pattern 1. Hallucination. Hallucination is when the agent produces output that is confident, fluent, and incorrect. A fact that doesn't exist. A policy that was never written. A product feature that doesn't exist. A name, date, or reference that is plausible but wrong. Hallucination is most common when the agent is asked for specific factual information it wasn't given in context. The retrieval system returns content that is partially relevant but not precisely matching. The system prompt encourages confident, complete responses without specifying what to do when information is unavailable. Diagnosis. Compare the agent's output against its source material. Did the information it stated exist in the context? If not, hallucination. Fix. Strengthen the system prompt instruction to acknowledge uncertainty. Improve retrieval quality so the agent has better source material.
Add an explicit rule. If the answer is not in the provided context, say so. Do not generate an answer from general knowledge.
Pattern 2. Loop stall. Loop stall is when the agent enters a cycle it can't exit. It calls a tool, gets a result. Calls the tool again, gets a slightly different result. Calls it again. The loop continues until the session times out or the context window is exhausted. Loop stalls happen when there is no stopping rule for the specific condition the agent encounters. A tool returns a result that the agent interprets as requiring further action indefinitely. 2 instructions conflict. One says continue, one says verify, and the agent alternates between them without resolving. Diagnosis. Review the decision loop at the point of stall. Which step is repeating? What condition should have triggered the exit? Fix. Add the missing stopping rule, or tighten the tool's success-failure definition so the agent receives an unambiguous signal. Pattern 3. Scope escape. Pattern 4. Tool misuse. Scope escape is when the agent takes an action or produces output that falls outside its defined boundaries. Answering a question it was told not to answer. Taking an action it wasn't permitted to take. Accessing data it had no business accessing. Scope escape happens when constraints are defined in the system prompt but not enforced in the orchestration layer. Prompts can be interpreted. Orchestration rules cannot. Fix. Move hard boundaries out of the prompt and into the orchestration logic where they are structurally enforced. Tool misuse is when the agent calls the right tool at the wrong time, with the wrong input, or interprets the output incorrectly. Symptoms. The tool returns a valid response, but the agent's subsequent action is inappropriate. Or the agent calls a tool repeatedly with slightly different inputs, searching for a specific result.
Diagnosis. Review the tool call sequence in the decision loop. Is the agent calling the tool at the right step? Is it correctly passing the output? Fix. Clarify the tool description in the system prompt, or add a few word shot example of correct tool use.
Building a failure log. For every production failure, log 4 things: the input that triggered it, the pattern it represents, hallucination, loop stall, scope escape, or tool misuse, the root cause, prompt, orchestration, tool, or retrieval, the fix applied, and the date. This log does 2 things. It builds a record of the agent's failure history that informs future design decisions, and it tracks whether fixes are working or whether the same pattern is recurring under different symptoms. A recurring pattern that has been fixed multiple times is not a prompt problem, it's a design problem. The failure log makes that visible. Failures are information production. Failures are uncomfortable, but they are the most valuable data your agent generates. Every failure tells you something about a gap in your design, a case the system wasn't prepared for, a constraint that wasn't enforced, a boundary that wasn't clear. Treat every failure as a contribution to a better system. Classify it, diagnose it, fix the root cause, test the fix, document the change. The agent that has processed 500 failures and been improved by each of them is far more capable than the one that was never tested. In the next lesson, we'll give you a decision tree for determining whether a failure is a prompt problem or an architecture problem, one of the most important distinctions in the entire course. 2 fixes, very different costs. When an agent behaves incorrectly, you face a fork in the road. Is this a prompt problem? Or is it an architecture problem? The distinction matters enormously. A prompt problem takes hours to fix. An architecture problem can take weeks. Choosing the wrong diagnosis sends your team in the wrong direction and costs time you can't get back. This lesson gives you a decision tree for making that call accurately. What is a prompt problem? A prompt problem is a failure that originates in how the agent has been instructed. The rules are ambiguous. An example is missing. A priority is undefined. The agent's behavior is inconsistent because the prompt leaves room for inconsistency. Key signals that the problem is in the prompt. The failure occurs on some inputs, but not others that seem similar. Adding a specific instruction or example makes the failure go away immediately. The failure is in the quality or style of the output, not in its fundamental logic. Different phrasings of the same query produce dramatically different results. What is an architecture problem? An architecture problem is a failure that cannot be solved by changing the prompt. The wrong tool is connected. The retrieval system returns the wrong content. The orchestration logic sequences steps in the wrong order. The memory system stores or retrieves incorrect data. The model class is fundamentally unsuited to the task. Key signals that the problem is architectural. The same failure appears regardless of how the prompt is written. The failure is consistent. It happens every time, not just on some inputs. Fixing it in one area breaks something else. The failure occurs in the decision logic or the tool results, not in the generated text. The decision tree. Question 1. Does the failure occur consistently across varied inputs or only on specific types of input? Consistent across varied inputs, likely architectural. Only on specific input types, likely prompt. Question 2. If you add a specific rule or example addressing this scenario, does the failure stop? Yes, prompt problem. No, architectural. Question 3. Does the failure involve the agent taking a wrong action or producing wrong content? Wrong action, likely architectural, orchestration or tool. Wrong content, likely prompt or retrieval. Question 4. Does the failure disappear when you test with a different, better supported model? Yes, model selection. No, prompt or architecture in the orchestration and tool layers. Why this distinction is particularly important at scale. At small scale, the consequences of a misdiagnosis are contained. A week of work in the wrong direction, recovered quickly. At production scale, a misdiagnosis has compounding costs. A team of 4 spending 3 weeks improving the prompt on an architectural problem. 3 weeks of failed deployments. Stakeholder confidence eroded. The fix, when finally applied, is straightforward, but the damage to the project's credibility is done. The decision tree takes 20 minutes to work through. Apply it before committing to a fixed direction. Document your diagnosis. Define what success would look like for each fix type. Only start work when the diagnosis is clear. When it's both, sometimes it's both. An architectural gap creates a failure that the prompt is then trying and failing to paper over. In these cases, the prompt fix gives partial improvement, but doesn't resolve the failure fully. That's a signal. When a prompt fix improves but doesn't resolve, look at the architecture. The architectural problem is real. The prompt is compensating, which works up to a point. Fix the architecture, then refine the prompt, in that order. Section 8 complete. You have built, tested, and diagnosed your agent. In Section 9, we measure whether it was worth building. You cannot measure what you didn't record. Every agent build eventually faces the same question. Did it work? And without a baseline recorded before the build, that question cannot be answered honestly. The comparison data doesn't exist. You can say the agent is performing well, you can say it's fast, You can say users seem to like it, but you cannot say it's better than what it replaced, because you didn't record what that was. This lesson is about building the measurement foundation before the agent goes live, not after, before. The 5 baselines worth capturing. Baseline 1, processing time. How long does the current process take, end to end, per transaction? Not the ideal time, the actual average, including queuing, handoffs, and review. Measure it on 50 real examples. Baseline 2, error rate. What percentage of current outputs contain errors that require correction or rework? Not near misses, actual errors that have a cost. Baseline 3, cost per transaction. What does the current process cost in human time? Multiply average processing time by the fully loaded hourly cost of the people doing it. This is the number the agent ROI is measured against. Baseline 4, customer satisfaction score. If the process is customer facing, what is the current satisfaction rating? NPS, CSAT, first contact resolution rate, whichever metric your organization already tracks. Baseline 5, throughput capacity.
What is the maximum volume the current process can handle per day without adding headcount? This is where the scalability case for the agent gets built.
How to record baselines. Don't estimate, measure. Even if measuring takes extra time before the build starts, the data is worth it. An estimated baseline is not a baseline, it's a story. For time-based metrics, use actual timestamps from existing systems. Support ticket timestamps, email send and reply times, process completion records. Don't ask people how long things take. People systematically underestimate. For quality metrics, review a sample of 50 to 100 recent outputs. Score each one against your quality criteria. That sample becomes your pre-deployment benchmark. Document the measurement method, how you measured, when you measured, and what sample size you used. Post-deployment measurement must use the same method, otherwise the comparison isn't valid. Choosing your primary success metric. Not all baselines are equally important. One should be elevated as the primary success metric for this specific build, the one most directly connected to the business case that justified the project. If the business case was cost reduction, the primary metric is cost per transaction. If it was speed, processing time. If it was quality, error rate. If it was customer experience, satisfaction score. Having a primary metric focuses the post-launch analysis. Secondary metrics give context, but the primary metric answers the question, did this build achieve what we built it for? When to take the first post-launch measurement? Not on day one. Day one is still calibration. The agent is encountering real production inputs for the first time. Some edge cases will surface. Some adjustments will be made. Day one data is noisy. Take the first post-launch measurement at 30 days. Enough time for the agent to encounter a representative range of inputs. Enough time for the initial calibration adjustments to settle. Enough data to produce statistically meaningful averages. Then measure again at 60 days and 90 days. The 90-day comparison against baseline is the data that drives the expansion, iteration, or stop decision we'll cover in the final lesson. Baselines as a cultural shift. Here's the longer-term value of this practice. Organizations that systematically baseline before AI builds develop a data culture around AI decision-making. Not faith, not enthusiasm, evidence. The second build is easier to justify because the first one generated real ROI data. The third builds faster because the organization has a measurement template. The culture shifts from we should explore AI to we deploy AI when the data says it's worth it. And that's the most sustainable position to be in. In the next lesson, we'll calculate the run costs, the ongoing economics of keeping the agent live. The cost is not just the API bill. The most common mistake in agent cost modeling is looking only at the model API cost. It's just a few cents per query. That's true, and that's not the whole picture. The true cost of running an agent in production includes the API fees, yes, but also the infrastructure it runs on, the human review time for supervised operation, the developer time for ongoing maintenance, the monitoring tools that keep it observable. Model it all. Component 1. Model API costs. Model API costs are priced per token. Input tokens processed plus output tokens generated. Your cost per interaction is average input tokens times input price per million tokens plus average output tokens times output price per million tokens. Example, an agent with a 2000 token system prompt, a 500 token average user message, and 300 token average response uses approximately 2,800 input tokens and 300 output tokens per interaction. At a typical mid-tier model price, that's roughly 1 cent to 3 cents per interaction. At 1,000 interactions per day, that's $10 to $30 per day. At scale, model cost is the easiest component to forecast, and often not the largest. Component 2, infrastructure. Component 3, human time. Infrastructure costs depend on how the agent is deployed. Cloud function, charged per execution, typically negligible per interaction. Dedicated server, fixed monthly cost regardless of volume. Managed platform, typically bundled with the platform subscription, but verify what's included. Add retrieval infrastructure if you're using RAG, vector database hosting, embedding API calls, storage costs. Human time is the cost most teams forget to model. In stage 1 of earned autonomy, supervised operation, every output is reviewed before it takes effect. That review time is a cost. If reviewing takes 2 minutes per output and outputs arrive at 200 per day, that's 400 minutes per day of human time. At the fully loaded hourly rate of the reviewer, calculate the weekly cost. It's often larger than the API bill. Component 4. Maintenance. Bringing it together. Maintenance costs are ongoing and often underestimated. System prompt updates. How often and how long do they take to write and test? Tool integration maintenance. API versions change. Model updates from the vendor. Do they require prompt recalibration? Test suite maintenance. The test cases need updating as the use case evolves. Estimate a monthly maintenance budget. For a simple agent, 2 to 4 hours per month is typical. For a complex one, 8 to 16. At your developer's hourly rate, that's a real line item. Sum the components. Monthly API cost, monthly infrastructure cost, monthly human review cost, monthly maintenance cost. That's your total monthly cost of operation. Divide by monthly transaction volume to get your cost per transaction. Compare that to your pre-deployment cost per transaction baseline. The break-even calculation. The break-even point is when the cost of running the agent equals the cost of the process it replaced. Below break-even, the agent is more expensive per transaction than the alternative. Above break-even, the agent is cheaper. Well above break-even, the economics justify expansion. Break-even also needs to account for the build cost. What did it cost to design, build, and test the agent? At what monthly saving rate does the agent recover that investment? The payback period, the time to recover the build investment through operational savings, is the number the finance function will ask for. Calculate it before they do. Cost modeling as a continuous practice. Model costs change, vendor pricing adjusts, usage volumes shift. The process the agent handles evolves. A cost model built at launch needs to be refreshed quarterly. An agent that was economical at launch may become less so if input volumes grow faster than anticipated, or more economical if vendor pricing drops, which it often does. The organizations that manage AI agent economics well are those that treat cost modeling as a quarterly operational task, not a one-time launch calculation. In the next lesson, we'll apply 4 ROI formulas to quantify the full value of your agent, not just the cost savings. Cost savings are only part of the return. When people talk about agent ROI, they usually mean cost savings. How much cheaper is the agent than the humans it's supplementing? That's a real number. It's also an incomplete one. There are 4 ROI formulas worth applying to any agent deployment. Each one captures a different dimension of value. Together, they give you the full financial picture of what the agent is worth. Formula 1, time saved. The time saved formula is the simplest. Hours saved per week equals pre-agent average time per task times pre-agent weekly task volume minus post-agent average time per task times post-agent weekly task volume. Multiply by the fully loaded hourly cost of the team handling the task. Example: a team was spending 3 hours per day on a task. The agent handles 80% of that volume automatically. The team now spends 40 minutes on the remaining 20%. Time saved: 2 hours 20 minutes per day. At the team's hourly rate, that's a real number. Annualized, it's a significant one. Important: time saved is only value if the freed time is redirected to something productive. If the team just uses the freed time to do less, the saving is theoretical, not real. Define how the saved time will be used before calculating this as ROI. Formula 2, error cost avoided. This formula captures the value of quality improvement. Error cost avoided equals pre-agent error rate times pre-agent volume times cost per error minus post-agent error rate times post-agent volume times cost per error. The cost per error varies enormously by context. A data entry error in a CRM might cost 5 minutes of correction time. An error in a compliance document might cost thousands in rework, legal review, and regulatory exposure. Estimate the cost per error conservatively. Even conservative estimates often reveal significant ROI from quality improvement alone. This formula is also useful for the compliance argument. Regulators and auditors respond to error rate data. If the agent reduces errors in a compliance-sensitive process, document that reduction carefully. Formula 3, revenue influenced. Formula 4, capacity unlocked. Revenue influenced applies to agents in the sales or customer experience path. The formula: post-agent conversion rate minus pre-agent conversion rate times volume times average transaction value, or post-agent customer satisfaction score minus pre-agent score correlated against retention data. Revenue influence is harder to isolate. Other factors affect it too. Use it as a supporting metric alongside the easier to isolate formulas. Capacity unlocked captures the scalability value of the agent. Before the agent, to handle twice the volume, you need twice the people. After the agent, you can handle twice the volume with the same team. The value of that unlocked capacity is the cost of the headcount you didn't need to hire. For growing businesses, this is often the highest value ROI formula. Not what the agent saved, what it made possible. Building the ROI summary. Apply all 4 formulas to your agent. Sum the value across all that apply. Subtract the total monthly cost of operation. Subtract the amortized build cost divided by the intended operational lifespan in months. The resulting number is your net monthly ROI. Present the ROI across a 12-month horizon. Month 1 may be negative, you're recovering build cost. By month 3 or 4, most well-designed agents are net positive. By month 12, the ROI is typically clear and defensible. A 12-month ROI summary is the document that justifies the next agent build. The ROI you can't fully quantify. There is a 5th category of value that doesn't appear cleanly in any formula: organizational confidence. The proof that AI agents can be built responsibly, deployed successfully, and measured rigorously. The internal credibility that comes from delivering what you promised. That confidence is worth something. It's what makes the second build easier to approve, the third faster to deploy, and the organization as a whole more capable of competing in an environment where AI capability is increasingly a differentiator. In the final lesson of this section, we'll use the ROI data to make the expand, iterate, or stop decision. 3 paths, 1 decision. Every agent reaches a decision point at 90 days. The data is in, the baselines have been compared, the ROI has been calculated, the failure log has been reviewed. 3 paths forward: expand, increase scope, volume, or capability. Iterate, continue at current scope, but improve the design. Stop, decommission the agent and redirect the investment. The wrong decision is to drift, to continue running an agent without consciously choosing its direction. That's how agents become expensive habits rather than valuable tools. The expand signal. Expand when the agent is consistently meeting or exceeding its success criteria. The ROI is positive and the payback period has been reached or is clearly in sight. The team handling the supervised operations component has confidence in the agent's outputs. There are adjacent use cases that share the same design patterns. Expansion can take several forms. Increase the volume of the current use case without adding new capability. Extend the agent to handle a second, related use case. Reduce the level of human supervision. Move from stage 2 to stage 3 of earned autonomy. Each form of expansion should be treated as a new mini-project with its own testing phase. Do not expand because the technology is impressive or because there's momentum in the team. Expand because the data supports it. The iterate signal. Iterate when the agent is performing but not at the level the success criteria require. The ROI is positive but below the projected target. There are specific failure patterns that are recurring and fixable. The user experience is functional but not good. Adoption is lower than expected. Iteration means targeted improvement. Identify the specific gap. Make a targeted change, test and measure the impact of that change alone. Don't make multiple changes simultaneously. You need to know which change is responsible for any improvement or any regression. Iteration is not the same as maintenance. Maintenance keeps the agent running at its current level. Iteration raises that level. Both are ongoing. Be clear about which one you're doing. The stop signal stop when the ROI is negative at 90 days and the path to positive ROI is unclear. The failure patterns are architectural, and the cost of redesign exceeds the value of the use case. The use case has changed sufficiently that the agent is no longer solving the original problem. The vendor or technology dependency has become too costly or too risky to continue. Stopping is not failure. Stopping a correctly scoped, well-tested agent that turned out not to deliver sufficient value is good decision-making. The discipline to stop is part of what makes the broader AI agent program credible. It signals that builds are evaluated on results, not on the sunk cost of having started. Making the decision. Bring the right people into the 90-day review. The person who owns the business process, the person who owns the budget, the person who built and maintains the agent, a representative of the users or customers who interact with it. Present the data, the primary metric comparison against baseline, the 4 ROI formula results, the failure log summary, the trend. Is performance improving, stable, or declining? Then make the call collectively and document it. The value of a conscious decision. The expand, iterate, or stop framework exists to prevent the most common agent failure mode. The agent that just keeps running because nobody made a deliberate decision about it. Running an agent past its useful life wastes money. Running an agent that should be iterated without improving it wastes opportunity. Failing to expand an agent that has earned it leaves value on the table. Make the decision consciously, based on data, on a defined schedule. That's how organizations get better at AI deployment over time, not by luck, but by building a decision-making practice around the results. Section 9 complete. One section left. From first principles to working system. You have covered a lot of ground in this course. 10 sections, more than 40 lessons, a complete framework for finding, designing, building, testing, and measuring an AI agent. This lesson draws those sections into a single connected arc. Not a summary, a framework you can hold in one view and return to every time you start a new agent project. Stages 1 and 2. Find it, define it. Every agent project starts with a problem, not a technology. Section 1 gave you the tools to find the right problem, the 5 business cases, the employee complaint test, and the profile of a strong first build. The output? A shortlisted use case with a legitimate business case. Section 2 transformed that use case into a design specification, the agent brief, the 4 elements of workflow, scope boundaries, a goal statement, the alignment test. The output? A document precise enough to build from and sign off on. Stages 3 and 4. Protect it, build it right. Section 3 added the protection layer, damage limitation, the reversibility test, earned autonomy, the scoping principle. The output, an agent that has clear limits, proportionate controls, and a path to greater autonomy as trust is established. Section 4 went inside the agent. 9 components: model, system prompt, failure patterns, context engineering, memory, tools, orchestration, decision loop, and interfaces. The output, a design that covers every functional element with no structural gaps. Stages 5 through 7. Choose, evaluate, validate. Section 5 gave you the build pathway decision, the 3-layer mental model. No code versus code first, the build versus configure matrix, and the diagnostic map for when things go wrong. The output, a clear technology decision with a contingency plan. Section 6 covered the special case of voice, a design challenge that looks similar to text but requires a completely different approach. Section 7 gave you the vendor evaluation framework, the scorecard, the terminology, the 2-week POC design. The output, a vendor relationship built on evidence, not enthusiasm. Stages 8 and 9. Test it, measure it. Section 8 covered the build and test phase. Build order, agent versus software testing, the 4-layer test suite, 4 failure patterns, the prompt versus architecture decision. The output, an agent that was built in the right sequence, tested against real criteria, and can be debugged systematically. Section 9 closed the loop. Baselines recorded before the build. Run cost modeling. 4 ROI formulas. The expand, iterate, or stop decision framework. The output, a measurement practice that treats every agent as an evidence-generating investment, not a leap of faith. The framework is your playbook. This is your playbook for every agent project you'll commission, oversee, or build. It's not academic. Every tool in it was designed to solve a real problem that real projects encounter. Every framework was built to prevent a failure that was common enough to deserve a named prevention method. Use it in sequence for new projects. Use the relevant sections when you're problem solving in an active build. Share the agent brief and alignment test with your team. Apply the earned autonomy framework to every agent already running. The technology will keep changing. The design principles will not. In the next lesson, we'll distill the entire course into the 10 decisions that make or break any agent build. 10 decisions. That's what this course is about. Behind every lesson in this course is a decision, a moment where a project goes right or goes wrong, based on what a leader or builder chose to do. This lesson names the 10 highest leverage decisions in any agent build, with the key question for each. Think of this as your pre-flight checklist. Before every new build, before every major change to an existing agent. Run through the 10. Make sure each one is answered. Decisions 1 through 4. Decision 1. Is this the right use case? The test. Can you map it to one of the 5 business cases with a specific, measurable outcome? If no, don't build. Decision 2. Is the brief precise enough to build from? The test. Can every member of the build team read the agent brief and independently describe what the agent does, doesn't do, and must achieve? If no, rewrite it. Decision 3. Have the scope boundaries been defined at the right level? The test. Have you listed every action the agent can take and classified its reversibility? Are hard boundaries in the orchestration layer, not just the prompt? If no, strengthen the constraints. Decision 4. Is the goal statement testable? The test. Can you construct a test that definitively proves whether the agent hit the goal or didn't? If no, the goal statement needs a measurable standard. Decisions 5 through 7. Decision 5. Is the system prompt production ready? The test. Does it pass the 4 failure pattern audit? Specific rules, sufficient examples, explicit stop conditions, no conflicting rules. If no, it's not ready. Decision 6. Is the model choice right for the task? The test. Have you tested a standard model against the actual task before committing to a reasoning model? Is the model choice driven by evidence, not default? If no, test before you commit. Decision 7. Is the build pathway matched to the requirements? The test. Have you scored the use case against the build versus configure matrix? Is the choice documented with the reasoning? If no, apply the matrix before starting the build. Decisions 8 through 10. Decision 8. Has the test suite passed its thresholds? The test. Do you have 30 or more test cases across golden path, edge cases, adversarial, and failure mode scenarios? Have all adversarial tests passed? Has the agent hit the defined quality thresholds? If no, don't launch. Decision 9. Have baselines been recorded before deployment? The test. Do you have pre-deployment measurements for the primary success metric and at least 2 secondary metrics? Is the measurement method documented for post-launch comparison? If no, measure before going live. Decision 10. Is there a 90-day review in the calendar? The test. Is the expand, iterate, or stop review already scheduled, with the right people assigned and the data requirements defined? If no, schedule it now. The pattern behind the 10. Look at the pattern across these 10 decisions. They are not technology decisions. They are not developer decisions. They are business leader decisions. Which problem to solve? How precisely to define the job? What limits to set? What success looks like? Whether to launch? When to review? These are the decisions that belong to you, the person commissioning and owning the agent build. The developer's role is to build what you specify. The model's role is to execute the logic you design. Your role is to make these 10 decisions well, every time. A standard worth holding. The organizations that build AI agents well aren't the ones with the best technology. They're the ones that make these decisions consistently. The ones where we don't build without a brief is a standard, not a suggestion. Where we don't launch without baselines is a cultural norm. Where we review at 90 days happens because it's in the calendar, not because someone remembered. Standards compound. The first agent gets better because of the standard. The second agent gets built faster because of the standard. The 10th agent gets deployed with organizational confidence that wouldn't have been possible without the 9 that came before. Hold the standard. In the final lesson, we'll set you up for what comes next. The course ends. The work begins. You now have a complete framework for building AI agents that deliver real business value. That framework is only valuable if you use it. This final lesson gives you a clear set of next steps, so the learning becomes action before the week is out. Step 1. Choose your first use case this week. Not eventually, this week. Use the employee complaint test to surface the highest friction, highest volume, most rule-based process in your team or organization. Run the profile of a strong first build against it. Score it against the 5 business cases. By Friday, you should have a candidate use case and a rough idea of which business case it maps to. That's enough to start. You don't need a perfect use case. You need a good enough use case with a clear problem. Step 2. Write the agent brief within 2 weeks. Take your candidate use case and write the agent brief. Use the template, 1 page, 6 sections. Get it in front of the people who need to sign off on it. The brief is the first real commitment. It turns an idea into a design. It surfaces disagreements that are better resolved now than after 6 weeks of build. And it generates the sign-off that makes the project real. 2 weeks is enough time to write the brief and hold the sign-off meeting. Don't let it take longer. Momentum is part of the first build's success. Step 3. Assemble a small, focused team. 3 people. Domain knowledge, technical execution, business accountability. You may be one of those 3, or you may be the person who finds the other 3. Either way, the team is small by design. Small teams move fast. Fast first builds build confidence for bigger second builds. Brief them on the course framework. Not every lesson, the key frameworks. The agent brief, the 4 elements, earned autonomy, the build order, the test suite structure. Get everyone using the same vocabulary. Step 4. Set a 30-day build target. A first agent build should aim for a working prototype, not a polished product, within 30 days. A working prototype means the system prompt is written and tested. At least 2 tools are connected and working, and you can run 10 golden path test cases and see the results. That's not a full production deployment. It's the evidence you need to make a go, no-go decision on investment in the full build. 30 days, one working system, real data, then the decision. Where to continue? The field of AI agents is moving faster than any course can track. The design principles in this course are durable. The specific models, platforms, and tools will evolve. Stay close to the primary sources. The major model providers publish research and capability updates regularly. The community of practitioners building and operating agents is active and generous with what it's learning. The most valuable thing you can do now is build something. Not study more, not wait for the technology to mature. Build something real with a real use case for a real business problem. Apply the framework, measure the result, learn from both the successes and the failures, and build the next one better. Thank you for completing this course. The hard part was always the design. Now you know how to design well. Go build.